I've got still a minute here, 8:59.
Okay, we'll just hang on tight then.
I've got my Starbucks mocha coffee cup right here.
I'm jealous. I didn't have time for my Starbucks run this morning, so I just have my drink, my iced tea.
We have people on already?
Yeah, we do. We have one, and then it's on the live stream.
All right, good morning, everyone. This is my Lajitas coffee cup from Lajitas, Texas. My favorite bird, the Roadrunner. In one of my favorite coffees, Starbucks mocha.
There you go. I had a pet Roadrunner when I was in college. It was wounded by the side of the road, and bleeding heart that I was, I stopped and retrieved it, and I kept it in my apartment in college for like a week.
Did it live?
Ultimately, no. I think it was really sick when I picked it up, and it sort of got better, but then it died. And I was very sad. Had a small funeral, invited my college friends. You ready to go ahead and get started?
Yes, well, it's 9 o'clock on the hour, so we want to get started promptly.
Okay.
I'd like to welcome everyone to the last day of SEG and our first presentation of our live presentations at our booth. We're delighted to have been able to offer these. I understand many of the booths do not have live presentations, so we are featuring these today. Along with Meet the Experts, another room we've set up on our microsite. So just please navigate to our Meet the Experts area after this if you would like to see more on what I'm about to present, and we'd be delighted to show you. This presentation, I'm Hal Green, by the way, and I manage marketing for Geophysical Insights. This presentation is an overview of the Paradise AI Workbench for seismic interpretation, which is commercial off-the-shelf software that uses machine learning and deep learning processes pardon me, to accelerate an understanding of the reservoir. Our business model, and a lot of people ask us this, is a service business, software business. We're a software business. We license the Paradise Workbench that I'm about to highlight here, but we also provide some consulting services to strategic customers. But our primary business is licensing what I'm about to share with you. So in terms of an agenda, real quickly, an introduction to Geophysical Insights, the company, and the Paradise AI Workbench, mainly about the latter. I'll offer a few case studies, single slide case studies in the application of Paradise, talk a little bit about GPU and hardware, and then how we get started. Now, a bit about Paradise first. Several solutions are enabled by the machine learning and deep learning processes that are available on the Paradise AI Workbench. So those include the identification and the ability to calibrate detailed stratigraphy, distinguishing thin beds below conventional tuning. We'll talk more about that momentarily. Classifying seismic facies, detecting faults automatically, interpreting DHIs, revealing faults and fracture trends in shale plays, and even estimating reserves and resources. The business case is straightforward. The business case for Paradise is optimizing field development by identifying economic reservoirs, especially in thin beds. Now, a single slide on the company. For those of you that may not know of us, Geophysical Insights was founded in 2008 by Dr. Tom Smith with the vision of applying machine learning methods to geologic interpretation. At that time, he was quite the visionary with respect to developing commercial off-the-shelf technology that would be eventually in the hands of every interpreter, geologist and geophysicist alike. Shortly after launching the company, Dr. Smith assembled a team of people to begin development of this next generation technology with this charge of enabling the software to be used by all interpreters. Paradise was then officially launched at the SEG, which happened to be in Houston that year, in 2013 rather, and has seen steady adoption worldwide and a continuous set of new capabilities added, which we will talk about. We talk about a workbench. Some may refer to it as a platform. Again, these are off-the-shelf, out-of-the-box capabilities that interpreters can apply, and they can apply together. They're not a fire and forget single application. This is an integrated workbench of solutions. Beginning up here in the upper left with attribute generation. We have a library of over 100 attributes that are available in Paradise. I'll give you some details on that momentarily. Color blending, or some may call it RGB blending, a method of selecting attributes. If we're dealing with multiple attributes simultaneously, we need to have a method of informing what attributes are appropriate for our region of interest, and we do. Multi-attribute classification. This is a machine learning technique. We're going to refer to this as SOM, self-organizing map, and there's an associated 2D color map with this capability to interact with the classification, machine learning classification results. Geobody detection, another method of machine learning that distills the classification results and creates a set of volumes that can be analyzed in greater detail. Two new deep learning applications, seismic facies classification and fault detection. These are supervised, by the way, using convolutional neural networks, so two supervised techniques. This, by the way, is unsupervised, multi-attribute. And a lot of these processes are being enabled by GPU computing. Machine learning, attribute generation in particular, and machine learning and deep learning processes are compute intensive, and we are moving many of these processes to GPU as it is appropriate to do so. We're also taking advantage of multi-threaded, multi-core machines, CPUs. There is a Petrel connector in Paradise that allows the seamless movement of information between Petrel and Paradise, and there is a scripting language which is used primarily by researchers. Again, our premise is this, and we urge you to check this against the presentations today, as well as our Meet Our Experts room. More can be seen in the seismic and well data using machine learning than traditional interpretation techniques or packages. Now, a bit about attribute generation. Paradise places over 100 best-in-class post-stack seismic attributes in the hands of general interpreters. It is enabled through this easy-to-use point-and-click thought flow that guides the interpreter through the generation of those attributes, and includes a comprehensive list of instantaneous, geometric, spectral decomp. The spectral decomp and geometric attributes in particular are from a library that we license from the Attribute Assisted Processing and Interpretation Group at the University of Oklahoma, led by Dr. Kurt Marfit, otherwise known as ASPE. Very well respected worldwide group in attributes. We license some of those into Paradise and make those available via a easy to use interface. Here you see on the right the groups of attributes that are available in Paradise, again with over 100. Instantaneous dip, structure, amplitude, similarity, curvature, spectral decomposition, and texture. We literally have one of the largest libraries available anywhere in attribute generation. Pardon me. I mentioned color blending, a useful technique, particularly for the blending of spectral decomposition attributes to identify stratigraphy and other features, as you see here on the right, with a channel-like feature shown and a fault. Attribute selection, if we are working in multi-attribute space and applying machine learning to multiple attributes simultaneously, we need a way of distilling or informing the interpreter what attributes are most appropriate or responsive to the region. And that technique is called principal component analysis. So as you see on screen, the top chart calculates something we call the eigenvalue, which indicates the degree of spread of the data across every inline in the field. Those are difficult to see in the black. Those are inline numbers in this particular example. And we have selected one of those inlines here for its eigenvalue and can expose in the lower left of the screen a chart that we call the eigenspectrum, which is a set of vectors that indicate the degree and spread of that data in attribute space. And in this particular case, we've given it 17 attributes. So what are we doing? We are identifying, using this technique, identifying the attributes that are most responsive to the region. And we are normalizing those attributes in this process and then comparing their relative contribution in the sense of variance, comparing their relative variance to an area of interest. It can be a single inline, it can be a multiple inlines. Pardon me. When we select the first vector here, that is telling us something about the spread and direction of the data, the first eigenvector, we see on the right instantaneous frequency, thin bed indicator, and dominant frequency are contributing double digits to that variance. The premise again is the greater the variance, the more energy, you could say the more information they are imparting to our region of interest. So we're going to use this technique to go from a larger set of attributes to a smaller set of attributes that are going to carry most of the energy and therefore be candidates for machine learning. So let's look at one example. Our first is a multi-attribute classification using the self-organizing map or SOM technique. This is a class 3 AVO setting. So this example happens to be offshore Gulf Coast, continental shelf. Note that the field is indicated in the amplitude at the top, right here, and some would argue it's visible. There are 2 gas wells drilled, one of which hit the reservoir at a gas oil contact and the other at oil water contact. The bottom 2 images are machine learning classification using multi-attribute classification or SOM. In each case, the interpreter assigned 25 classes. One had found that 25 classes were optimum to distill the stratigraphy in this image or in this region as compared to those wells. And you see the results here. With all of the classes highlighted, we see very clearly the gas oil contact and the oil water contact as DHIs, flat spots, direct hydrocarbon indicators. If we empty all but the 3 classes of interest, we're going to refer to these as neurons, as you see here in the bottom image. We turn off all the other classes except these 3, which are highlighting the reservoir and the flat spots. We can very clearly see those flat spots again. And on the right, note that there is a character change at the edge of the anomaly or flat spot, which are highlighted here and here. These are down to 1 sample thick. So this illustration points to 2 results from Paradise that I mentioned earlier. The ability to detect thin beds and reveal direct hydrocarbon indicators. Again, on the ability to detect and illuminate stratigraphy, this example is in an unconventional setting, specifically the Eagle Ford. And in this area, the Eagle Ford formation is only about 30 milliseconds thick, or about 1 wavelet. On the left, you see the original seismic amplitude volume, and on the right, the results of the multi-attribute classification using the SOM technique. In this case, the interpreter assigned 64 classes for an 8x8 neural map. The different neurons in the 2-dimensional map, again, on the right, correspond to the colors of the seismic facies. And this indicates very clearly 64 different classes, the ability to discriminate thin beds due to this stacking effect when analyzing multiple attributes simultaneously. Now, once we have the classification results, we want to analyze them further in terms of geobodies. There is a technique within Paradise, therefore, to detect the geobodies among classes and we see the results of that here. This happens to be a project offshore Colombia. We see the display of geobodies from machine learning, which are corroborated with well control, as shown in the image. So while not visible at this level, the geobodies are comprised of individual voxels, again, which correspond to single samples. We can do more with geobodies in Paradise. Given bend spacing and a few other geologic parameters like velocity, net to gross, porosity, and water saturation, the value we can generate the volumetrics on those geobodies down to and including an estimate of hydrocarbon pore volume, as you can see here right on the right-hand side of our chart. So the value of geobody calculation, really of the workflow from machine attribute generation, machine learning, and geobodies, is to gain a quick sense of the shape and size of reservoir. Now we'll show the results of two new deep learning applications that use convolutional neural networks. I just spoke about unsupervised machine learning techniques. These are supervised machine learning techniques, both available in Paradise. Here's an example of an automated fault detection result. The seismic survey is from the Great South Basin offshore New Zealand. On the left, we see the original seismic amplitude volume on which the fault detection was performed. And then on the right, we see the fault probability from the CNN-based fault detection done in Paradise, which took, by the way, about an hour to do. Note the greatly improved fault continuity, resolution, reduced noise from the CNN fault detection method. The value simply is, from this application, is time. This aids the interpreter by reducing the amount of time to develop a fault probability volume. And from here, further analysis can be done in Petrel. Likewise, Paradise has a seismic Facies classification also based on convolutional neural networks. Here we see an example of the output from seismic Facies classification, a supervised form of learning. You see the Facies classification tool is used to identify where features like multiples, stacked channels, or chaotic zones exist in a region. In this case, the interpreter has selected 8 different desired facies a priori. In other words, this is supervised, and then has applied this tool across a region to produce these results, which are displayed at the intersection of an inline and cross line. This is powered by GPU. I mentioned that earlier. The deep learning models are compute intensive, so this is one of those capabilities that is on GPU. The classification results provide well-defined, clean geobodies, as you see here, on which we can also perform volumetrics and take those back into Petrel for further analysis. Now, a lot of people ask us, how do we tune the machine learning results in concert with or in corroboration with well control? This is new capability that allows for the user to extract most of the seismic volume along the wellbore, and these volumes include seismic attributes, machine learning, or deep learning results. The value of this new capability is in the ability to optimize the machine learning results with respect to the wells. And this example shows the SOM and well in a 3D view along the wellbore portrayed in the well cross section. A gamma ray log is also shown here on the right, and the ability to see your extractions with other log curves allows for this optimization of the machine learning results, again, with respect to the well logs. We can set up a set of these views for multiple wells, in fact, in an area. These are examples of some of the extractions that can be done using the well log extraction tool. When the curves are created, Many different types of metadata are stored with them, including the color bar that is active for the parent attribute. So when the curve is brought in for display, the fill is automatically applied with the same color bar, taking a lot of the effort out of the work of building these color bars. These can be done very quickly. Paradise, pardon me, has maintained a robust connector to Petrel that features a drag and drop interface. And Paradise 3.4 has several enhancements to that connector, including the support for Petrel 2020, as you see in the title of this slide. This enables this particular version enables the ability to bring the log curves from Paradise back into Petrel. This is important, of course, because once you've done the work of identifying the machine learning results that best correspond to your well logs, you want to bring that work back into Petrel to include in your overall interpretation of the region. Now, I've mentioned GPU computing at several points. Geophysical Insights continues to work with Nvidia in a cooperative way to migrate certain compute-intensive processes to GPU where it makes sense. We have moved some spectral decomp and geometric attributes to GPU processing. I mentioned the CNN supervised machine learning processes like seismic facies classification and fault detection, also on GPU. Early tests have indicated dramatic results, some 50x reduction in the compute time for spectral decomp attributes. And we're planning a steady release as appropriate, taking advantage of multi-core CPU operation and GPU operation where it makes sense. Paradise runs typically in a client-server configuration, and that, by the way, can be either on-premise or using cloud as an infrastructure. Here you see a diagram of a typical client-server deployment, perhaps across an asset or an office with a Paradise server shared by multiple clients on a network. Geophysical Insights has partnered recently with Dell to offer an appliance that consists of hardware, software, and installation. Since Paradise runs either on-premise or using cloud as an infrastructure, and we have customers using both, we can work with our customer as they prefer to host Paradise. However, some of our customers do prefer an on-premise solution, and for those that do, we have offered this appliance, which is for 5 concurrent users, as you see here, and has some 56 physical cores, 3 Nvidia Tesla P40 cards, etc. All solid-state memory, a very robust machine that we've tested thoroughly in our offices, and quite confident of its ability to very effectively support 5 concurrent users. The key takeaway, pardon me, from this overview is the following. We've talked about attribute generation, color blending, attribute selection, multi-attribute classification, well log visualization, automatic fault detection, seismic facies classification, and the Petrel connector. I hope we've highlighted how Paradise incorporates both machine learning and deep learning technologies to refine an interpretation. And we have shown how every interpreter, a geologist or geophysicist, can apply Paradise to accelerate their work while extracting greater insights from seismic and well data. So I invite you to continue to take advantage of the presentations through the course of today, our live presentations here, as well as the opportunity to meet the experts in our Meet the Experts room. With that, I'll be glad to take any questions.
Just as a brief reminder to everybody. Oh, there's an echo. Okay. You can put your questions in the chat box, and Hal will be happy to answer those verbally. Alternatively, if you're watching this on the YouTube live stream, you can post your questions in the comment stream, and we'll get those as well.
And Laura, if you wouldn't mind just reading the question, please. If there are any.
As soon as they come through, I'll be happy to. We'll give it just another minute more because I know the live stream is about 30 seconds behind the Teams broadcast.
Don't be shy, folks.
Okay, very good. Well, if that's it, like as Hal said, feel free to jump over to the Meet the Experts page, and you're welcome to stop by and visit with us and get your questions answered there. Thank you very much today, folks.
Thank you. Have a good day.
in the comments section, and we'll get those as well. So without further ado, Fabian, here you go. Fabian, I think you might still be on mute.
Hello.
There you go. Now we can hear you. Go ahead.
Okay. Thank you, Laura, for the introduction. Good morning to everyone. I want to thank every one of you for being in this presentation. My name is Fabian Rada. It's a pleasure to be here today to talk about how we correlate some volumes generated with Paradise with discrete well-log data using statistical tools. In this case, this is a question: what were the interpretation objectives and the geologic setting? The intention was to detect the lithological contrast of a reservoir and map the extension of the best neurons. It means the neurons that have the best petrophysical values for V-shale, effective porosity, and water saturation. The reservoir, in this case, is dolomized calcareous breccias that lays on the upper Cretaceous section, are carbonates, and the depth in the area of interest ranges between 3,000 and 4,000 meters below sea level. In this slide, I want to show you the general workflow that we commonly use. And the first box at the left implies the selection of several attributes that respond to the detection of or are useful for detect lithological contrast. They are common instantaneous attributes as attenuation, envelope, instantaneous frequency, Hilbert, the amplitude, relative acoustic impedance, the envelope second derivative, the sweetness, and thin bed. So all of these attributes respond to lithological contrast. We know this because we had done several tests and for the bibliography, no? Also we applied principal component analysis in this step in order to select the most contributed attributes in order of variance, and of course the knowledge about the use of attributes and the knowledge about the geological setting of the zone. So we run several sums, and the second step is to review the sums using vertical sections, sculpted volumes, or horizon probes, geobodies, stratal slicing, so we can see the patterns in the data, in the results, in the classifications, and select maybe a couple of volumes or some volumes, so we can extract those volumes along the well paths and see how these neuron numbers correspond to several properties, yes, and understand the behavior of those properties and and how they are distributed in the area. I mean, with the sum volume classification. The next step is to prepare the data to do this calibration using bivariate and multivariate statistical analysis. It means contingency tables, chi-square test, and cluster analysis, and the review of the petrophysical properties. So at the end, we will have a calibrated sum volume that could be ready for use. Yeah. In the second step, as I show you in the workflow, we review the self-organizing map or SOM results in vertical sections. And this is an example in this slide. You can see that in black you have the amplitude traces or wiggles. So you can see that the top of the reservoir is a peak, but with the SOM classification, the colorful type of data that you can see in this section, you can see more detail than you be able to see with this amplitude. So towards the top of the reservoir, this one, you can see the samples grouped by neuron 11 in this color yellow and ochre yellow. And in the first analysis were related with calcareous sandstone that overlies the fine calcareous breccia in this Cretaceous section or units that are the most productive, BK and BK1, and we're grouped by neurons 1 and 2, the yellow and the pink that you can see in this section, yellow and pink. Okay, towards the base of BK2 unit, the facies are medium calcareous breccia, not fine as at the top. And in some places, the neuron number 23 and 24, this pink, kind of pink and blue, kind of pink, and in some places blue, stand out, and which being of such different numbering from those numbers identified in the upper sections or units of this reservoir. And these changes seems to be responding to possible differences in rock quality. And we have a question why we use the statistical tools with the machine learning results that came from Paradise. But, well, because we wanted to link the SOM results that are discrete values and compare with the well-logged data. So we think that the statistical tools are a good way to explain the relationship between the SOM volumes and well-logged data and how petrophysical properties were discretized by SOM results. This work that I'm presenting today is based in a methodology published in September edition in First Break magazine of the EAGE in 2019. And this article is available for you in Geophysical Insights webpage. So what process and tools we employed and what were the results? The first step was to build a 3D grid. In this grid, each cell must have the same dimensions as original seismic data, sampling interval and bin size, of course. And the second step is to assign the values of the SOM volume to this grid in order to visualize the vertical proportion curve of the SOM, this figure that I'm showing you. And the second objective is to create a discrete property that could be extracted along the wells, yeah, the well paths. So the third one is to apply the statistical analysis itself. So in a qualitative way, we based on the expertise of interpreters, you know, trying to see patterns, or maybe I'm talking about not using statistics at the beginning. This is the common way. You see the number of the neurons along the well path and trying to match with the well log information, well logs, production data, cores, etc. So this is qualitative, and the interpreters could have a good level of expertise, and several times we are successful, yeah. But we were looking for a quantitative approach, and please let me show you in the next slides how we do this process. So in order to run a more detailed analysis, we export the logs, continuous and also the discrete logs, including the sum classifications as last format, and the sample interval for well logs, including the sum classification, is half a feet or 0.15 meters. So we export these last files with this information and prepare the data in order to be analyzed using an in-house development that we call cross-table and cross-table Petrel in order to run the statistical analysis. So part of this statistical analysis is the chi-square independence test, and the chi-square test was created by Pearson more than 100 years ago, and this is frequently used in health and medicine or biology or social sciences. And in this slide, I will show you an example of a medical case, but the goal is to analyze the relationship between two qualitative variables. It means that the values of the variables are not numeric, are not scalars, they are categories, as occurs with the neurons of a sum generated with Paradise. Okay, this is a medical example. As you can see, you have several medical or type of treatments, treatment 1, 2, 3, and 4, and you have 3 levels of responses obtained from the experiment. In this case, the patient responds in a worse way, or the same response, or a better response to the treatment, to the type of treatment. Okay, so in this contingency table, you have one variable in the columns and the other variables in the rows. So this is the observed frequencies of the experiment, the real observed frequencies. So you have to establish 2 hypotheses. The first is the null hypothesis that refers that the variables are independent. The alternative hypothesis is that correspond to the dependency of the variables. So how these hypotheses are contrasted, or the null hypothesis is contrasted. So you have the frequencies that would be expected to be obtained if the 2 variables were independent are calculated and compared with the observed frequencies. So you have to build a expected frequencies table, and this table is easy to construct. You only have to do these simple mathematical operations between the marginal frequencies in the columns by the rows and dividing by the total of samples. So you obtain the expected frequency for these cells. You have to obtain the expected frequency for the entire cells in the table. This is another example, another cell. So you have to multiply this value by this and divide it by the total, and so on. It's important to verify that in the table of expected frequencies, the percentage of cells with expected frequencies lower than 5 is less than 20% of the cells. A higher value will invalidate the chi-square test, and the statistical methodology allows to collapse or regroup contiguous categories or cells with expected values less than 5. Yeah. Continuing with this medical example of chi-square, we calculate the critical chi-square value with a confidence level of alpha and 6 degrees of freedom. So we compare the values, and the null hypothesis says if the calculated values is bigger than the critical value, so you have to reject the null hypothesis and accept the alternative hypothesis. So in this way, we demonstrate that the response to the treatment and the treatment are related. Yeah, the variables are dependent, in other words. So let me show you how we adapted this statistical tool to our geoscience world. So in this slide, I show you two contingency tables built from the count of net reservoir property by neuron. Yeah, at the left, we have the contingency table of lithological contrast sum versus the net reservoir categories. Net reservoir has two categories. The first one, net reservoir itself, that has the capacity, the storage capacity, the porous space, and the no reservoir part of this. Yeah. So at the right, you have the expected frequencies. So you have maybe the count of neurons observed. For maybe neuron 1, you have 43 times the no reservoir category, and 3, 5, 7 the net reservoir. And maybe you have in the expected frequencies 55 and 345. Yeah, the values are closer. And of course, we are looking in this example for neurons that have good counts in net reservoir. Yeah, because they represent neurons that are the reservoir. So maybe neurons 1 and 2 are reservoir, maybe the 3 no, because has null value here. Maybe the 5 is almost the same amount, so it may be a mixture of things. So you have to interpret these results and you know, find a geological sense of this evidence. Next, in this slide, I show you two contingency tables. At the left, we have the contingency table of this lithological contrast sum. You can see in some slides the word MAO. MAO means self-organizing maps in Spanish. So these contingency tables represent the facies by neuron. So in this example, you have at the left the observed frequencies, and the best properties facies in this reservoir are medium and fine calcareous breccia. Yes. At the right, you have the expected frequencies. And again, if you look at the details, neuron number 1 have a lot of amount in or counts in fine calcareous breccia, the best facies in this field. Number two is pure fine calcareous breccia. Number 3, medium, but you can see the frequencies also, the number of times that you count some properties by neuron. So you can say if maybe number 3 have lower frequencies, and maybe you have to investigate a little bit more in your data in order to have a criteria. It means that if makes sense to the geological significance in this area. Okay, another contingency table built from a continuous property, in this case porosity. The first thing that we have to do is to regroup this continuous variable, the porosity, into classes, in this case by ranges, and so you will be able to compare categorical values with neurons, yeah, discrete values. So in this case, we rearrange or regroup the porosity by those range: null, low, medium, or high porosity. Okay, and again, the neuron number 1, maybe you have these counts, null and low categories of porosity, but you have a little bit more proportions in medium and high categories of porosity. The same behavior occurs with the number 2, and maybe you have the inverse or the opposite trend with the neuron 5. You have null, higher nulls and low counts. Sorry. Okay. This is an easier way to analyze the contingency tables, and I mean all those graphs that I'm showing you came from the contingency tables, and that you already see in the previous slides. So in this case, the proportion of each category for net reservoir, for facies, and for porosity regroup by ranges are shown, and it's easy to see the observed frequencies for neuron 1 in yellow, 2, 8, 11, 12, 16, 20, 22, and 24. Yeah, for net reservoir. And also you can see the same neurons have facies in fine and medium calcareous breccia. And in the chart in the bottom left corner, yeah, for medium and high values of porosity, the green and the yellow bars. We want to look more about the petrophysical properties, behavior from the well logs, and how correspond to our sum classification neurons. So you can see maybe the distribution of those petrophysical properties: effective porosity, water saturation, and V-clay. And you can see how some neurons maybe are reservoir and correspond to the net reservoir part, but maybe have higher or high values of water saturation. So you have to be careful, and this is the way we do to to inspect the petrophysical values or evaluations against the some neurons. Okay, with the same data from contingency table for net reservoir in this case and the sum, we build a radar or a spider charts. So you can see if the observed frequencies on the some neurons are scoring high or low within the net reservoir and no reservoir properties or categories. In this case, you can see the proportion. Of course, you have this kind of chart show you the magnitude, and you can see the neuron 1, 2, 3, 4, so on. And you can see in the table the number 1 has a big proportion of net reservoir, the number 2 also, and so on. Also, we might generate these same graphics, bars or radars, charts from the expected frequencies if the two variables were independent. And finally, we computed the experimental chi-square for this data, and it's bigger than, this is the experimental, and it's bigger than the theoretical chi-square value. So you have to reject the null hypothesis and accept the alternative, so the variables are dependent, or the sum for lithological contrast and the net reservoir property relates each other. Yeah. Also, we calculated the likelihood ratio and the p-value for the chi-square and p-value for likelihood ratio with this significance level, these degrees of freedom, 17. We have I think English is the statistical power. This one, and we have two types of error type 1 and error type 2 of these chi-square distributions. So investigating with 3 different association indices like Kramer, the corrected contingency coefficient, and the Shupro coefficient, we have for this data a moderate relationship. Yeah. Okay, in contingency tables with nominal variables, once it has been established that there is a significant association between two variables using the chi-square or likelihood ratio statistics, and the association has been quantified with some index, the Haberman residuals constitute the best tool available until now to accurately interpret the meaning of the detected association. The different percentages that we see in this top right corner can help us to distinguish the possible association patterns, but it's the Haberman residuals that allow us to interpret the relation between the variables. So it is not enough to look at those z-scores values that are greater than, in absolute value, than 1.96. So values greater than this value indicates a larger relationship between the categories. Yeah, it means that the larger the absolute value of the residual, the larger contribution of this cell or this neuron to the magnitude of chi-square. So I mean that under the null hypothesis that the two variables are independent, the adjusted residuals will have a standard normal distribution. It means that with a mean of 0 and a standard deviation of 1. So the adjusted residual that is more than 1.96 indicates that the number of cases in that cell is significantly larger than would be expected if the null hypothesis were true. This is with a 95% of certainty. And an adjusted residual that is less than minus 1.96 indicates that the number of cases in that cell is significantly smaller than would be expected if the null hypothesis were true. In other words, cell-by-cell comparison of observed and estimated expected frequencies help us to better understand the nature of the evidence. And cells with large residuals show a greater discrepancy than we would expect if the variables were truly independent. So there are several neurons that the magnitude of the Habermas residuals is too long, so something is going on with these cells or neurons. Yeah. This kind of graphics, the Habermas residuals or the percentage of the absolute values, Habermas residuals, the percentages, and the observed frequencies can be generated as spider or radar charts. And as the zone classification is for lithological contrast, it means the attributes selected respond to lithological contrast. We checked the count of net reservoir and no reservoir by each neuron. So you can see the color map. You can see neuron 1, the 2, 3, 4, and the net reservoir is the bar at the right. The no reservoir proportions at the left. Neuron number 1, 2, 3, etc. So you can see that some neurons have predominance of net reservoir, like number 1 or 2, but maybe this neuron is the opposite. Or some neurons have similar counts. Yeah, this is a way to observe the behavior of this property. Sorry. Also, you can see the porosity histograms by neuron. Neuron number 1, neuron number 2, neuron 3, and so on. And you can see the distributions of, in this case, porosity by neuron, and get more information from the data. Yeah, the same occur with Michel. In this carbonate reservoir, you have this vertical dotted line that represents the cutoff value. So you can see that in almost all the neurons, you have distributions below this cutoff value, and is at least in Mexico, this is the behavior. Yeah. Finally, we review water saturation distribution by each neuron to get a different perspective of the data, because at the end of the day, we want to find hydrocarbons, no? So in water saturation, you have the vertical dotted red line that represent the cutoff value, and you can see that several neurons are okay, but maybe others are mixed or are, as I'm indicating with the laser point, distribution with high values of water saturations. So you have to be careful, or we have to be careful, in order to say if those neurons are really representing the good part of the reservoir. Another way to see the behavior of the data is through cross plots. Of course, in this case, we have porosity versus V-shale for each neuron, neuron number 1, neuron number 2, neuron number 3, and so on. All the neurons that were connected or extracted along the well paths in the reservoir or in the reservoir, within the reservoir. Sorry. So you can see another cross plots. In this case, water saturation and V-shale versus V-shale by neuron. Water saturation versus porosity. But you can build the graphs, cross plots, box plots, bar charts, spider charts, using another properties, maybe Poisson or VPVS ratio or acoustic impedance and so on. Yeah. Okay. In this slide is very interesting graph because it's another way to analyze the behavior of the neurons through the percentiles of the petrophysical values. In this case, the first one is V-shale, and you have this black horizontal dotted line that represents the cutoff value. As you can see, this is the legend for the neurons. Not only the neurons, be aware of the frequencies or the number of times that each neuron has this property, V-shale. So maybe you have 400 for number 1 or almost 200 for the number 2, but the number 3 only has 5 samples. So this is a way to make a further analysis and apply the criteria in a good way. So maybe number in V-shale, as you can see, most of the neurons has the maybe percentile 70 are with or represents V-shale volumes lower than the cutoff values, but maybe this one have this portion from the percentile 75, you have some data above the cutoff value, so you have to be careful with this neuron. This is the number, help me, the number 17. You have only 20 times this property. Okay, the porosity, again, the dotted horizontal line is the cutoff value for porosity. And you know, in this reservoir, few neurons are anomalous, yeah? Water saturation. You can see neuron number 1, the yellow, and 2, this pink with a little dot or circle, are very, very low values of water saturation. But maybe you have another neurons that have another trends, so you have to be careful. So using the radar charts, we can see the same properties, and this is another tool to analyze the behavior of the petrophysical values or properties by neuron. Neuron number 1, 2, 3, 5, and so on. For some interpreters, radar charts are an easier way than histograms to analyze the data. Yeah, but of course, they represent in a different way the same pattern. Okay. As we have been seeing so far, we use different graphics for analysis like bars, radar charts, histograms, among others, that are useful to understand the behavior of the neurons as a function of the petrophysical values from well-log data. Additionally, we wanted to apply a tool from multivariate statistics known as cluster analysis that allows us to identify the neurons with higher relation or similar characteristics. In this case, from two properties, petrophysical properties, porosity and volume of shale. And they are conformed by the cluster number 1 and the cluster number 2. The number 1 is remarked in blue, and the remarked in blue at the top of this table have the lowest values of B shale, are very clean, and porosity values ranging between 4 and 17%. The cluster number 2, the neurons in red, have larger values of B clay with respect to cluster 1, and have porosity values ranging between 0 and 8%. So it's very important to note that the frequency of the points for each neuron, as we saw in the previous slides. So we have to be aware of neurons with low counts of samples. It means in this case number 9, 23, 21, 13, and 17. And we must identify if those neurons have geological meaning or not. We ran a second cluster analysis, but this was conducted using 3 petrophysical properties. They are V shale, porosity, and water saturation. And we found 6 different groups. The cluster number 2 with neuron 1 and 8, that is in this place, and the cluster number 4, neurons 2 and 20 and 2, are the neurons that have very clean values of V shale, good porosity values, almost 10%, and saturation values of almost 30, or in this case 15 or to 18. Yeah, they are another neurons that are separated in a separated cluster and represents bad portion of the reservoir. So with this technique, we figure out how the petrophysical values correspond to the classified volume. But we, in our methodology, we don't only use the statistical analysis. Also, we use different visualization techniques as plan views, vertical sections, 3D perspective views, vertical proportion curves, cross plots, box plots, radar plots, among others. And it's very important the geological knowledge in the area of interest, in order to understand a little bit more the reservoirs that we are studying. As a conclusion, well, for property prediction, we analyze the sum classification volumes along the well path and against the well log data using statistical and geostatistical tools, and it was possible to perform the calibration and better understanding of the sum classification. In this case, the lithological contrast detection is an example, and in this case, we demonstrated that respond to net reservoir, facies, and porosity regrouped by ranges. As I said, other properties from well logs could be treated as explanatory variables. It means maybe net pay, VPVA's ratio, Poisson, among others. And also other sums volumes could be treated as response variables, like maybe as some classification using attributes that only responds to pay volume or fluids, or maybe porosity or fractures, among others. And finally, I would like to thanks to Hal Green for this opportunity, for inviting us to present, and his constant support. Also to Ivan Marroquin for fruitful technical sessions, and Tom Smith from Geophysical Insights for their contributing comments and suggestions. Also thanks to Laura Curil from Alberta for her support, and my gratitude to my colleagues David, Marco, and Cesar for their constant effort daily. And finally, I would like to express my public gratitude to Reynaldo for his help in this process of continual learning. I think we got to the end of this presentation, and if you have questions, please go ahead. Thank you very much.
Thank you very much, Fabian. That was excellent. Now, ladies and gentlemen, if you would like to type your questions into the chat box, you're welcome to do that, and Fabian can answer them at this point. We'll wait just a few minutes because I know the YouTube live stream is about 30 seconds behind the Teams broadcast.
Oh, okay. Thank you. I'm looking to another screen that I have in.
Well, you can see them if you click on the chat in the side.
Oh, yeah. Thank you. Thank you for your comments. Thank you. Thank you to Ivan, Tom Smith, and Carl David.
So there's a question
Ernesto.
here.
Hello, Ernesto.
Hector asks, could you please expand on the technique used for the cluster analysis? Hierarchical clustering, for instance.
Okay. Hello, Hector. We use the method known as the median, and we use in English use the metrics known as standardized Euclidean distance. So we have several another methods, and this is you have to test several because not only the method but also the metrics, because some of them works better with certain type of data. But this is part of the work. You have to analyze the data, and in this case, the cluster analysis techniques represents to us a good tool to understand a little more the behavior of the data. Yeah, that this data was in some way previously classified by the sum algorithm in Paradise. Yeah. I open to more communication or discussions, maybe via email or cell phone, for sure. It will be my pleasure. Okay, thank you. You're welcome, Jinkai.
Well, we'll wait just a few more minutes.
Oh, let me show you my. Oh, sorry, I got lost. You see my screen?
Yes, we can.
Ah, okay. This is my email. Want to write me? You can find more information in the Geophysical Insight webpage, geoinsights.com. Thank you, Mr. Chi.
Okay, well, at this point, I'm going to go ahead and end the meeting, and we'll start up the next one, which is Mr. Chi presenting on an integrated fault detection workflow at 11 o'clock, so in 8 minutes. So feel free, if you're still on this call, to go ahead and jump over to the next one and join us there. Thank you so much, Fabian. I appreciate it. You guys have a great day.
Thank you. Thank you. Have a nice day, everyone. Thank you.
Hey, did that work?
No. You want to try again?
Okay, let me try that again. So,
There we
how
go.
about
Now we can see it. Yes.
Cool. Let me open up that.
Perfect. All right.
Okay.
Let me just insert a comment here real fast. If you have questions during the presentation, you're welcome to type them in the chat box, and Jay will be able to answer those verbally at the end. Alternatively, if you're listening on YouTube, then you're welcome to get them in the comments feed, and we'll get to those as well. So there you go. Take it away.
Thank you, Laura. So good morning, everyone. Thank you very much for joining us at the Geophysical Insight live presentation. So in this presentation, I will introduce an integrated fault detection workflow. So I'm Jie, the research geophysics. And here's my outline of the presentation. So at the beginning, I will introduce what is this workflow and we'll talk about what is the challenges. I will go through the CNN-based fault detection workflow, which include the 3 major steps. So first is data conditioning, and the second step is computation of the same fault probability. And the third step is the same fault probability post-processing. Then I will show the 2 applications. One is just the same fault post-processing, and the second application is including the seismic data conditioning and the same fault post-processing. That is my conclusion. So now let's go into the introduction. So as we already know that identical faults are very significant to characterizing and finding the potential oil and gas reservoirs. So recently, most of the traditional fault detection methods include the interpreters manually picking and using the seismic attributes, or the image processing method, or deep learning, such as the CNN methods. And usually seismic amplitude data exhibiting the good resolution and the high signal noise ratio are keys to identify structural discontinuity, which means that first we need to preconditioning the seismic data as good resolution as possible, so that this can be more easier to identify the more accurate structural features. And in recent years, the deep learning application of a convolutional neural network has been proved that it can perform very well on fault detection. And usually, if you're using the synthetic trained fault detection models, that can be without any human-computer interactive works. And in this study, I will show an integrated CNN-based fault detection workflow to construct the fault images that are sufficiently smooth for subsequent fault automatic extraction. So here's the first step of our workflow. So I will introduce what is the seismic data conditioning. So on the left figure, this is a vertical slice through the seismic amplitude data. So this is the original seismic amplitude data, and it's offshore data. We can note that there are a lot of the major faults go through from the 0.2 second to 1.7 second. And in the middle, we know that there is a very chaotic zone that is a mass transport deposit or mass transport complex. You can see that if the fault penetrates this chaotic seismic facies, that faults are difficult to be detected. And also along this MTD facies, there are a lot of random noise and migration artifacts and some incoherent noise also, like stratigraphic discontinuity along these edges. And also there is other very important, significant noise is acquisition footprint, especially in the shallow area. And this is the example showing that seismic data conditioning, and the red figure is through the same inland. And note that this data set, this seismic amplitude is after data conditioning. And compare the left and the right, we know that most of the random noise from here has been suppressed, and also including the footprint right here has been surprised. And also the fault, the sharpness of the fault has been preserved and as sharp as the original seismic data. So that's what we're going to do for the seismic data conditioning. After seismic data conditioning, we will think about how we can also improve the fault imaging from the edge detection attributes or the convolutional neural network fault probability. Then we will introduce a technique called fault image post-processing. So on the left figure, this is a time slice at 1 second through the coherence attributes. You can note that there are two salt domes, which one on the left and one is on the middle right. And MTD, the mass-terminal complex species, are still in this area. And what is the fault image post-processing going to do is just we want to enhance all the fault, but also suppress all other noise. The red image is showing the same time slice, but after the fault post-processing. And note that all the fault has been enhanced and has been highlighted, but other noise like a salt dome MTD, the discontinuous feature has been suppressed. Then let's go to the seeing-based fault detection workflow. This figure showing the whole workflow of this integrated fault detection workflow. So the input is just the seismic amplitude, and after the first step for data conditioning, we will compute the same fault detection fault probability. Then we will got the volume of a fault probability. Then input this fault probability into the fault enhancement using a directional Laplace of Gaussian filtering. Then with the directional scalarization, we will get the final enhanced same fault detection result. Well, let's go into the first step. And what is the steps of the data conditioning in our workflow? Actually, we have two subtle steps of the data conditioning step. So first is we're going to apply a KS-KY filtering, and the second is a structure-oriented filtering. So the difference between these two filtering is that KS-KY filtering is used for the footprint acquisition, footprint suppression. So KS-KY filtering is used to suppress very strong acquisition footprint. And structure-oriented filtering is used to suppress incoherent noise and some less strong random noise. So for KS-KY filtering, this is an example showing the KS-KY filtering, and this figure is a time slice through the seismic amplitude data. And the red figure showing the most negative amplitude curvature computed from the original seismic data. And note that this data set contains a lot of the noise, especially this very regular footprint, acquisition footprint. And then we're going to using a filter, which is the median filter, to filter the most negative amplitude curvature by enhancing those acquisition footprint. So we want to using this most negative amplitude curvature as a base map to highlight all the footprint acquisition footprint. And this imaging showing the seismic amplitude, the time slice through seismic amplitude in KS-KY domain. So note that the signal, flattened signal, or the reflector, is located along the origin, which is in the center, is pointed by the yellow arrow. And other anomalies like faults, channel, or other stratigraphic discontinuity can be spreading along the KX axis and KY axis. And the black arrow indicates the service edges. It's not the fault, this is the edges. And the white arrow, this one and this one, indicate the footprint anomalies on the seismic amplitude data. And the red figure showing the time slice through the most negative amplitude curvature in the KS-KY domain. Note that all the white arrow is indicate the footprint, and all the signal flattened to the reflector located in the region, and the black area still indicate the fault edges. Then we can use in the filter and threshold and define the regularization window to compute the magnitude of the anomalies. Then use a threshold to filter out all these periodic anomalies, which is the footprint, and we can subtract those footprints from data, get the filter data. For the structure-oriented filtering, there is 3 major steps. So first is compute the covariance matrix from a single waveform which best fits with each origin seismic traces. So along this seismic, this figure, which showing the 5 seismic traces. Note that we will find the best fitted waveform and then replace those original waveform with this best waveform, also with a cross-correlation coefficient. So in the second step is compute the best coherent waveform by the first eigenvector of the covariance matrix. Then cross-correlate this eigenvector with each sample vector, and we will get the filter data. So after the data conditioning, we will go into the same fault detection. We will compute the fault probability volumes. So we use this figure showing the Paradise deep learning fault detection patterns, these modulars. In the Paradise Paradise deep learning or machine learning modulars, we have 5 algorithms. First 2 is PCSOM, which is used for seismic Facies analysis. And we have Geobodies modulars, and also we have a deep learning seismic Facies analysis. So the last one is deep learning fault detection. This is what we will use here. And we will select a pre-trained model. In this example, we only use the conservative serial model to detect a major fault, which can result in the less false positive. So in my previous talk, in my previous presentation, I talked about the difference between the conservative model and the other aggressive model. So if you are interested in that, you can watch my previous presentation. Then after we compute the same fault probability, we will go into the last step, which we call the CNN post-processing, including a directional Laplace of Gaussian filtering application, and also the application of a directional scalization. Then we got the final same fault detection result. So the fault enhancement and scalization is 2 steps of the fault post-processing. So on the left figure is showing asteroid, and note that it's very similar to the anomaly on the either seismic attributes or same fault probability. So we will build the second moment tensor to find the orientation of the fault anomalies. Then apply a directional Laplacian of Gaussian filtering to enhance along the direction that is perpendicular to the fault, which means in the fault enhancement step, we enhance the fault along the fault anomaly. The directional is parallel to the fault. And in the scalization step, we will do the scalization along the direction that is perpendicular to a fault. So here is a vertical slice showing a seismic example. So note that the fault enhancement is enhance the fault along this fault, parallel to the fault. And the scalization is to scalarize fault perpendicular to the fault anomalies. Then we can compute the 2 different fault attributes. The first attributes we call the fault deep magnitude, and the second one is fault deep azimuth. Here is a figure showing that time slice, and the green box showing a fault. Then we define the 2 attributes. That is the fault which is perpendicular. Sorry, it's the fault that perpendicular to the normal angle, which is a deep magnitude, and so it's normal down is a deep magnitude. And if the project of this perpendicular vector 3, the project of the perpendicular vector 3 on the time slice, and the angle between this projection and the north direction is a default deep azimuth. So the V3 is the third eigenvector of the second moment tensor from that first probability. Then let's see some example of the whole workflow. So in the first example, this is data acquired in the offshore Texas, and the major structure is a strike slip fault, which is right here and right here. And some subtle fault has around 1.5 seconds to 3.5 seconds. And in the very deeper area, there is some false positives. So note that this is just the same fault probability computed from the seismic amplitude data. And then we apply a post-fault post-processing method. So first is a fault enhancement. Let's compare this original and after enhancement. Note that the major strike slip fault, the gaps between them has been filled, and all the fault has become much more smoother and continuous, especially right here and here. Another area is this area in the shallow area, some noise and also some false positives can also be enhanced. So we will apply a fault scalation in this data set. And here is showing the same fault probability after the fault enhancement and the skeletonization. We can note that all the fault has been skeletonized and some random noise has been suppressed. All the major faults right here, one major fault, the two major faults, which been skeletonized, and also the minor fault has been skeletonized. Here is the time slice through the 0.8 second. Note that this AA prime is the previous line, which is located here. And this time slice is through the same fault probability, it's original fault probability. And this is the one with the fault enhancement. Note that fault in the time slice become more continuous. And that after scalation, fault has been very sharper. Note that this major fault become very sharper. All these major faults become very sharper. Then we compute the fault deep magnitude and fault deep azimuth using the co-render techniques. The left image is showing the same A prime through the seismic amplitude co-render with seismic fault with the same fault probability. Then the right imaging showing the co-render of the same fault probability with the same fault deep magnitude and azimuth. Note that we're changing the color bar for the deep magnitude from the 90° to the opacity, to the transparency, and 0 to the opacity, which is similar to the fault probability. And then we can make the background to be black and the low angle deeping fault to be gray, and then make the azimuth color bar to be saturated. Note that all these faults can be separated by the different color, which means it can be separated by the different fault azimuth and fault deep magnitude. And then this is showing the time slice through the 1 second. Note that this is the major strike slip fault. And it's corresponding on our co-render fault deep magnitude, fault deep azimuth, and fault probability. Note that even this is one major strike slip fault, the fault azimuth is variance through this time slice. Then we will go into the next example. So this is the data acquired in Australia in the one basin, the deep water basin. Note that there are many major faults right here. In the shallow area, there is very strong footprint, and in the deeper area, the data is very noisy, and the signal almost gone right here. So note that this is a new line BB prime and through the seismic amplitude data. This is the original seismic amplitude. Then in the first step, we applied our data conditioning workflow, which is here. And one is the original seismic amplitude data, one is conditioning seismic amplitude data. compare these two, we know that we have surprised a lot of footprint in the shallow. Note that this is some noise has been surprised after this data conditioning workflow. And also the fault has become much sharper after the KX-KY filtering and structure-oriented filtering. So that the fault becomes sharper. And other random noise in the middle area has been suppressed as well. And in the deeper area, the fault anomaly has been preserved as sharper as the original seismic amplitude data. Then next, we compute the same fault probability on both the original seismic amplitude and the conditioning seismic amplitude data. This figure showing the BB prime through the seismic vertical amplitude data corrender with the same fault probability computed from the original seismic amplitude data. Note that the same fault probability highlights most of the fault, but in the deeper area, there is contained some false positive. For example, right here, and here. The next figure showing the same slice, but the same fault probability is computed from conditioned seismic amplitude data. Let's compare these two. Note that a lot of false positive has been surprised. Those false positive is computed from the same fault detection, but after the data conditioning, a lot of false positive has been surprised. Next, we apply the fault enhancement to this same fault probability computed from the conditioning seismic amplitude data. And also as well scalation as well of this one. Note that this is the original same fault probability computed from conditioning seismic amplitude. And this is the same fault probability after fault enhancement and skeletonization. Note that all the fault has been skeletonized and the resolution of fault become better, and the residual false positive has also been skeletonized. For example, right here, and other fault has been enhanced. Some manual fault has been enhanced, and the false positive right here has also been skeletonized. And we also compute the same fault probability, deep magnitude, and the deep azimuth, correct them together. Note that the one fault is oriented to the north direction, which is equal to 0. 0 is to the north, and the fault, this major fault, and this parallel fault is about oriented to 150 degrees. So note that using this corrender of same fault probability for deep magnitude and for deep azimuth, the fault become much more easier to be interpreted. Now we move to the seismic time slice. And this is the original seismic time slice at 0.68 seconds. And this is the same fault probability computed from original seismic amplitude. Note that there contains some footprint, either in the median area, not very shallow. There are still some footprint, and some other the false positive right here. And we compare the same fault probability compute from the original and compute from the conditioning seismic amplitude data. Note that this footprint anomaly has been surprised by the data conditioning step. And other random noise or false positive has been a little bit surprised. And then we apply the post-processing on the same fault detection. This is a post-process the same fault probability. This is original same fault probability computed from conditioning seismic amplitude data. Note that all the faults become much more sharper and much more continuous. And the last figure showing the post-process the same fault probability correlated with fault azimuth and fault deep magnitude. Then we go into the conclusion. So the objective of this project was to surprise the noise and other stratigraphic anomaly subparallel to reflector dip, and also the sharpen the fault and other discontinuity that cut the reflector. So the result is a preconditioning the fault imaging for subsequent automatic fault extraction. So we apply a 2D continuous wavelength transform-based acquisition footprint suppression, and the results showing that all the major footprints, major acquisition footprint as artifact can be surprised, then compute on the same fault detection results. And the principal component, edge-preserving structure-only filter, is also applied to suppress cross-cutting noise as well as the sharpened fault edges. And the condition amplitude volume is then fed to a pre-trained same model, which is using the Paradise software to compute the high-resolution fault probability volumes. Then in the post-processing steps, a Laplacian Gaussian filtering is applied to the original same fault probability to enhance the fault imaging. Then the final result of the fault probability volume is very favorable with respect to traditional human interpreters generated on the vertical slice through the seismic amplitude volumes. So in the acknowledgement, I would like to thank the Geophysical Insight for the permission to present this research work. I would also like to thank Cooperative and Geoscience Australia for providing the data that has been using in this research. Then thank you all for joining us, and thank you very much. Any questions?
Thank you very much, Jay. We appreciate that. It was a great presentation. So if you would like to show the chat, or not show, but if you want to jump over to the chat on your screen, you're welcome to ask questions there. And Jay will respond to those verbally. If you're on the YouTube live stream, you can post them in the comments and we'll get them. We'll wait just a few minutes because I know that the YouTube live stream is about 30 seconds behind this presentation.
Okay. Yeah, thank you, David. Thank you, Yingkai.
So after this, if you have a little bit of time in your schedule in the day, you're welcome to run over to our Meet the Experts page, also accessible from the same site that you access this presentation from. And there we have several rooms where our staff are hanging out and waiting to answer your questions or give you a demo or whatever, however you may like to connect. So I'd encourage you to drop by over there and visit them over lunch. All right, if there aren't any more questions, we can go ahead and close out this meeting. I hope you guys have a great rest of your afternoon and come back for our presentations a little bit later. The next one will start at 1 o'clock. Thank you very much, Jay.
Yeah, thank you. Thank you, Laura.
section, and we'll get those as well. So without further ado, let's get Deb started.
You want me to go? Good afternoon, everyone. I'm having a little technical difficulties on my side because I can't hear anyone, but hopefully you guys can hear me just fine. As Laura said, my name is Deborah Sakry. I'm a consultant in the Houston area in Texas. I've been out on my own for about 30 years, and I've been using Paradise for about the last 8 years. So what I want to discuss with you today is how I've been using Paradise, or the SOM classification process in Paradise, to find oil and gas for myself and my clients. Now, I won't read all of this because there's a lot to it, but basically Paradise is a pattern recognition and a cluster analysis tool, similar to classification technology used in Wall Street and in the medical profession. The key element here to understand and what differentiates Paradise from other machine learning applications out there is, one, this application I'm using is totally unsupervised. I don't know what natural patterns are in the earth when I go in, so I'm going to let the computer tell me what it sees down there. Secondly, instead of using wavelets like many applications have in the past, we work on sample statistics. So we're looking at every sample along a trace in a 3D or 2D line. And that's very important because that allows us to see subtle variations in the Earth's surface, subsurface, that the normal wavelet information won't let us do. And thirdly, we use multiple attributes at one time instead of working on just an amplitude or instantaneous phase or one attribute at a time. So we're using compounding and understanding the Earth's subsurface better by using a lot of different attributes that are designed to find different things about the subsurface. There are some caveats here. It is not one and done. It is a process that you do through trial and error. You can send in too few neurons and look for classes and run the risk of breaking up the patterns or aggregating the patterns together for a more regional or coarse view, or you can use too many neural classes and run the risk of breaking up the patterns into pieces too small to accurately interpret. So that's a key element here. Now, when we're looking at the wavelet, you may have, depending upon the frequency of your data, you may have a wavelet that's 30 or 40 milliseconds long. And by looking at sample statistics, say if you have 2 millisecond sample resolution here, you're going to be parsing that data 20 times as much. So instead of just a peak or a trough or a zero crossing, you're going to be looking at everything along a 2 millisecond sample window. And why we use multiple attributes is when we're going through.
Deb?
Yeah, Laura?
Deb, we can't see your screen.
I can't hear you. Can you type? I am sharing my screen. I'm not sharing my screen.
Now you are.
You want me to stop and start over and try to rejoin the Teams meeting? Here's Teams. Okay. Can you see my screen now? Okay. So sorry about that, folks. Again, technical difficulties. That's what I get for living in the country. But why we use multiple attributes is that along each point in the 3D, each attribute has a little tiny different piece of information. And so when we are looking at the wavelets, basically, of these different attributes, they're giving us a different number each time. And we take all those samples from all those numbers from all those samples, and throw them into an attribute cloud and basically look for the natural clusters that form from all these attributes and all that information. And that's millions and millions of data points. So when it comes back to the Earth, because each sample has an X, Y, and Z value to it, and we know the bin spacing of our 3D, and I'm going to get my pointer going here. We know the bin spacing of the 3D, and we know the sample interval we've used. Say in this case it's 1 millisecond. So we have what I call chiclets, but they're basically voxels that represent neural patterns in the Earth. And there's no interpolation between the data points as there is in amplitude data. And the tuning thickness now is, in the sample statistics, is really based on the interval velocity of the rock from which the sample's taken. So if you're working in the classic world, you might be able to see thinner bits of information than you would if you're working with classics, which are much faster. So just bear that in mind, because I'll be showing you examples of both. Now, a lot of people will ask me, how do I determine which attributes I'm going to use in my recipe? And I call it a recipe because I love to cook. And when you're making up a group of attributes to go into a SOM analysis, I just call it a recipe. So what we do in that case is we start off with something called principal component analysis. And this allows us to take a large group of variables or seismic attributes and find out which attributes are really more pertinent to the zone of interest that we're working in. In other words, it's a way to find the most meaningful seismic attributes. Now what we do, and this is just an example of two attributes here. I have attribute A and attribute B, and the first principal component in the principal component analysis is the longest variable amongst the data points, okay? And the second principal component is going to be orthogonal to that. But that's fine if you only have 2 or maybe 3 attributes, that our brains can handle that. But what happens if you're using 8, 9, or 10 attributes? And we can't see in that many dimensions, but the computers can. And the result is, here is a case where I put in 12 attributes. And the first eigenvector, or the dimension along which there's the most information, gives me a subset of 4 attributes which account for more than 93% of the data found in all 12. Now the beauty of what Paradise does is it goes through in each inline and it does a separate PCA analysis along the inline direction. So you can choose a line that goes through a good well and look at the attributes that come out of that. Or you can choose a line that goes through a dry hole and look at the difference between the attribute or the reaction to the Earth that the attributes are giving you. And the second eigenvector, now you've already taken out 93% of the information in the first 12. So the second highest eigenvalue is these 3 attributes are going to be basically 81% of the remaining information that the first ones didn't get. So here's a case where I've gone in with 12 attributes and I've come out with 7 that comprise most of the information that I'm going to need to investigate my zone of interest. So without further ado, I'll get into some of my case histories. This first case history is an example of a thin bed analysis that I did for a client. And he had an engineer buddy bring him a deal where he said, okay, I've got 3 wells down here on the southwest side, which didn't produce very well, but they had some production. And then all the way up this fault block up here, I have a really good well that at the time had made about 460,000 barrels of oil. Now in the engineer's mind, this was a blanket sand that covered the whole fault block, and all we had to do was lease in between and drill wells. Well, my client, let me turn my phone down. My client came to me and said, okay, what do we do to sell this deal? And I said, well, the first thing you're gonna have to do is buy the 3D. So he bought me about 8 square miles of 3D and let me do the mapping. And what I discovered is that the really good well came from about 7 feet of perforations in a sand called the Alabel sand. That's a Frio sand in this county. And you can see right here that the perforations tie just to a very wispy little amplitude. You can't even map it. It's so faint. And one of the things that's critical when you're working in sample statistics, you have to be really accurate with your synthetics because you could tie to the wrong sample. You can get away with sloppiness in the wavelet world, but you cannot get away with it in the sample world. So in this case, you can kind of see a little peak event here, 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 and then by the time you get back over here, that peak event's gone. And below it, the reflectors are pretty flat, but you can see kind of an arcuate form over this little amplitude. And my first thought is that maybe that's a sign of differential compaction. So here's an expression of that wispy little amplitude as you're going along that fault block. Now what I've done here is I could map the trough above it, and then I could flatten on that trough and pull it flattened time slices. So this black line right here actually represents a flattened time slice about 17 milliseconds below the mapped trough. So I went in with my recipe. This is classic, so I use things like sweetness, relative acoustic impedance, instantaneous phase, instantaneous frequency, especially, and thin bed when you're going in looking for thin sands in the Gulf Coast. And what came out of it was this kind of blue and green pattern right here, which to me represents or looks like some kind of offshore bar. It has a very finite end on one side and on the other side. And again, along the strike line, you can see that how this kind of color pattern comes and goes along the fault. Here are the three poor wells at one end. Here's the good well at the other end. Now, when I flattened on the time slice and looked at it, I could see that, yes, it did appear to be a little bar, a little thin offshore bar in the Frio. And while the engineer tried to explain the lack of production at the three wells at the southwest end by saying that they were mechanical failures, in actuality, they were just on small pieces of the sandbar, and therefore they had limited reservoirs. Here's the good well that's made 460,000 barrels, and I'm interpreting this kind of orange zone coming through this as a possible tidal channel cut. And if that's the case, then that has compartmentalized the production of the good well away from the rest of the bar, which could be significant. Here's a blow up of it. Now, this red line here represents the 80-acre production unit that was formed around the good well. So my client came in 467 feet off of the production unit, which is a legal location in the state of Texas, and drilled a well. And what we found is we found 6 feet of Alabel pay that's connected to this bar right here. And it came on at about 250 barrels of oil a day and 1.1 million cubic feet of gas. Now we had 4 feet of pay in this grub sand right here behind pipe. When I turn on just the neurons that represent the bar, and so instead of using a flattened time slice, you can see the distribution of the sand in that part of the 3D. So here's the full distribution of the sands, and here's the good well. My client drilled a well right along in here, and then here's some of the poor wells down here on the southwest side. Here's my recipe that I used. Envelope, imaginary part, instantaneous frequency. I used the amplitude volume, relative acoustic impedance, thin bed, and then Hilbert. Now, bring everyone up to date on what's happened since then. Here's the good well. It's now produced 7.4 BCF and 946.8 thousand barrels of oil in the last 3 years. After my client drilled the well 467 out of their production unit, the original operator came along and drilled a well 1,700 feet away from the original well. And to date, that well's made a little over a half a BCF of gas and 56,000 barrels of oil. My client's well at this point has produced 1.5 BCF and 154,000 barrels of oil. And then my client drilled a new well right here where this star is, mainly for the grub sand, but they did find production in the Alabel as well. And to date, that well has produced a little bit more than a half a BCF and 53,500 barrels of oil. So far, this little offshore bar, which covers about 1,000 acres, has produced 1.2 million barrels of oil and over 10 BCF of gas. Another play that I've had luck in, or you know, I'd rather be lucky than good since I'm Irish, but this is a play in southern Oklahoma I've been involved in since 2013. And the play type is a thin lower Pennsylvania sand that laps out against structure or against coming up from the shelf. And what I found is you can map the reflector that represents where the sand is all the way up to a termination point, but that may not be where the sand actually terminates. So this little green pattern right here actually represents this lower Pennsylvania sand. And we have now gone a third leg down from these two wells, haven't found a water limit yet. So this thing seems to be productive all the way to the south at this point. And the idea behind it is we have a series of these lower Pennsylvania sands. Some of them never get out of the basin and get up on the shelf and stay wet. Then there's one or two sands that we can chase that come out of the basin and come up and terminate against structures or terminate against the shelf edge. And that's what we're playing. And then there's upper sands which go off of 3D and we don't know where they're going to be productive. But all I do is map the occurrence and then again flatten on that time slice and then just go along the termination of where these sands are present and drill wells. Now, in the field that's next to the one that we're developing now, I have used this as this has been successful 17 out of 18 wells. So it's not quite like shooting fish in a barrel, but it's pretty darn close. One of the first discoveries I had using Paradise was in Wharton County, Texas. And I was looking at a 3D that a client had given me. And he said, you know, I've picked out everything I can to drill. If you can find something else, you can have an override and we'll put it together. And I said, fine, that works. So I was looking at an old, well, not necessarily old, drilled in the 90s, lower Wilcox field right here that had produced at that point about 80 BCF and 800,000 barrels of oil from sands anywhere from 13 to 15,000 feet deep. And my usual list of suspects for attributes that I use in the Gulf Coast is I use sweetness to help me find sand versus shale. And then I use average energy, which is an attribute out of Kingdom, to help me see where there might be hydrocarbons. So this field was showing me, okay, the really good wells have both sweetness and average energy to them. And here's what the sands look like. The lower Wilcox sands are pretty nice and thick. For Wilcox, they have pretty good porosities. And then there's a whole bunch of middle Wilcox thin pays behind pipe in many of these wells. So one of the things that I did, and I've had 3 discoveries using what we call low probability. And all we're doing when we say probability is looking at the data points in each cluster. Now, it goes against the brain to say low probability because we want high probability of success. But the probability really means how close these data points are to the center of the cluster. So the ones that are on the feather edge of the cluster and still part of the cluster have the lowest probability of being in the center. I mean, that makes sense. So we can adjust. We create a low probability volume, and we can adjust with a slider how many data points we actually want to see. Sometimes it's 10% or less that really show up hydrocarbons, because if you're using AVO anomaly, attributes or hydrocarbon indicator attributes, many times your low probability data points will actually be your AVO anomalies. So this was the first major discovery I had using this methodology. So what I've done here is I have superimposed the low probability part of it in white on top of the classification. Over here is just the low probability. And what I found when looking at this deep field is that the low probability anomaly was centered over those wells which were 10 BCF or greater. Now there's a series of wells in the middle. This feature has a little saddle in it and then comes back up. The wells in the middle were in the 5 to 6 BCF range, and then I had another series over here of 10 BCF or greater wells again. So that tells me that the low probability is really picking up on good concentrations of hydrocarbons. Looking at the rest of the 3D, and I noticed that there was an upthrown block to this deeper field, which had a lot of the same characteristics as the deeper field. It had a nice sweetness response, meaning there were sands there. It had a good average energy response, which in my mind tells me that there's hydrocarbons present. And most of all, it had, using the same recipe that I used on the lower field, it had a pretty good area of low probability anomaly. And here's my low probability color bar. You're looking at 0 to 100%. So I just took the last 10% and colored it white, and then just kind of filled in the rest of the colors with, random colors. But the white is what you want to see stand out, because those are your most anomalous data points. So I went to the owner of the 3D and said, okay, I think I found an area that you've overlooked, and showed him what I was talking about. And we took this exhibit to Nate and sold the deal in 4 showings. Here's the sweetness comparison between the down-thrown field and the up-thrown field. Here's the average energy comparison between the down-thrown field and the up-thrown field. And then here's my low probability anomaly in the 10 BCF or greater, and up here in the up-thrown field. It doesn't matter that this is upper Wilcox and this is lower Wilcox. The rock property responses are what Paradise is picking up. So they probably have comparable porosities and permeabilities, and certainly in my mind appear to have hydrocarbons in both areas. And then I did a neural study that covered both the up-thrown and down-thrown, so that you can see the low probability data points in the down-thrown field, again, separated by a saddle in the middle. And then you can see the low probability neurons that are responding in the up-thrown side. So the down-thrown field ended up being about 800 acres. The up-thrown side ended up being close to 1,000 acres. We drilled the well in 2016 on this first anomaly right here. And we had to deviate the well because the lady who had the acreage would not let us drill on her land. She wanted to protect trees and animals, so we had to deviate underneath her fence. This is the result of the first well, and you can see I had multiple pays. We perforated and fracked this very lowest sand, which is still producing after 4 years, and it's made over 2 BCF and 30+ thousand barrels of oil. So if you think about that, and the fact that the low probability was finding 10 BCF or better, it's easily conceivable that we'll have another 8 BCF out these remaining sands. Now here's the mud log associated with that section, and I had some, and we're just producing out of this lowest sand right now, so we still have all these good shows to go through. The well went on production. Again, it's still producing, and went on 1164 cents choke, making 3.2 million cubic feet of gas a day and 150.6 barrels of condensate a day at 6,700 pounds of flowing tubing pressure. Now this is a little movie I had set up, but it's not working right now, but that just shows the flare. And again, what's interesting is because of the price collapse we've had, my partners are no longer interested in drilling this stuff right here. So we're just producing from this one well, and we've let the leases go on all the rest of it. So if anyone's interested, contact me. Now, this is a situation where, again, it's in Wharton County, and because I've worked this county so long, I pretty much have my recipe down pat for what I'm looking at. And in this particular case, I'm looking at an area where I know that number 7 and number 8 are key neurons to production. And what you're seeing here is you're seeing a down-thrown field that was found in the 60s. You're seeing a new well that was spud, I guess it was late 2018, and now they've drilled this piece right here in 2019. And then another old field also discovered in the 60s. So this is my key element to say that I'm heading in the right direction. And again, I'm looking at low probability anomalies. So here's the newer discovery. This well was drilled after the 3D was shot. This is Mohat. All these wells were drilled and depleted before the 3D was shot. Now, there's always going to be residual hydrocarbons, so that's why you're still seeing low probability information. And then this field is also depleted. But I have a nice low probability anomaly in my prospect area, upthrown from the depleted field. And this well right here, that's a dry hole, is structurally low to my anomaly, but did have a show in the upper Wilcox. And what I'm looking for here is I'm looking for a very unique stack of attributes, because when you have hydrocarbons in the system, they're going to affect the seismic response above the field and below the field. So here in my depleted area, I've got this green pattern, and I've got this yellow, orange, and white. Over here is the white and yellow, which are my neurons number 7, number 8 that I'm looking for in the area. And I've got a really good solid green pattern below it. So this tells me that I have hydrocarbons intact, whereas this kind of sketchy pattern tells me that I'm seeing signs of depletion. So one of the things that Paradise can do, as I mentioned early on, is we know the bin spacing of the 3D, and we know what our sample interval is. So we can take this information and create what we call Geobodies, which give us volumes of information. And if we know the water saturation, the porosity, we know the interval velocity, and the net to gross ratio, we can calculate how much hydrocarbons we expect out of any one geobody. So this is an example of where I've gone into the depleted field, and I've looked at the total production of that field, which was 4.123 BCF and 98,000 barrels of oil. Obviously, they over-drilled it back in the 60s, but they didn't have the seismic. So I converted everything to a gas equivalent by multiplying the oil by 7. And so my total gas equivalent is 4.8 plus BCF of gas. So I looked at the geobody that represented the production in the old field, and I took the pore volume and divided by 43,560, which is how many square feet you get in an acre. And I used an estimated recovery factor of 1,000 MCF per acre foot. And I ended up with an estimation of reserves of 4.659 from this geobody, and the actual is 4.809. So that's only a 4% error in what I could calculate from the geobody versus the actual production. So being comfortable with that low percentage of error, I took those same numbers and estimated the geobody up here. Now, it's going to take more than one well, obviously, to fully capture all the reserves potential here. But my total reserves for that geobody is 15.2 BCF of gas. Now, 8,900 feet, one string of pipe, drilling completed about $2.3 million. Even in today's gas prices and oil prices, that's very economic to drill. The only problem with this prospect is it's already leased, and I can't get to the leases. So, oh well. And just to show you that it had some really good indications, even without the Paradise, is here's my sweetness anomaly. Here's my average energy anomaly. It looks like a little channel or a little bit thicker sand upthrown here. I had an energy absorption volume, and I also did a relative acoustic impedance, again, where you can see a little bit of a channeling or sand thickening. And the blue indicates lower acoustic impedance, which could be an indication of porosity. So even without Paradise, which to me I use as risk reduction, it had good hydrocarbon indicators to help support the anomaly. Now, finding hydrocarbons is really important, and that's what we're all trying to do. But sometimes we ought to be looking at why we shouldn't drill a well and use this kind of classification process to avoid dry holes or subeconomic wells. And that's the case with the next two examples I'll be showing. This first example is deep South Louisiana. As you can see from the depths here, 21,000, 21,500, so very, very deep in South Louisiana. Now, my client, this well was drilled in 2013, and it was a huge discovery, coming on at 30 million a day and 2,000 barrels of condensate a day. And my client had acreage in an adjoining fault block to this discovery well. And they thought that it was a lookalike, and so they went out on the market and they just about had the deal sold to drill this 21.5 well when we had the price collapse in 2014. So they shelved it. All the acreage expired. And then last year they decided, well, maybe it was time to put it together again. And so they came to me this time and said, okay, before we spend $30 million to to put the acreage together and promote it and go ahead and get a well drilled. Can you tell us whether you think it's going to be valuable or not, or whether it's going to be successful? So I said, okay. And I took the data and looked at the good well. And you can see here, I've done a little blow up. This is a 300-foot thick Chris R massive sand from which this well is producing, and it's still productive. And what you'll notice is this limestone cap that's on top of this block. Now, by the time you get out of this fault block and cross over into my client's fault block, that limestone is gone. So that was red flag number one for me, because you have to have a good seal. And these deep, highly pressured reservoirs. And a lot of times what I'll see happening in these reservoirs is that if there's no really good seal, that there's a lot of vertical percolation and leak off. And in fact, coincidentally, there is a field above this structure, shallower in this area. So that was my first clue as to there being a problem here. And when I did my Paradise analysis, and I used the far angle stacks in this case to create my attributes because I was looking for AVO type responses. What I noticed is, as I suspected, that there was vertical percolation and leak into the fracture system that was in the limestone. So much so that it changed the properties, the rock properties of the limestone itself. So this green pattern, this green neuron right here, which is on top of the big massive Chris R sand, is indicating where the reservoir is in my mind. And what you'll notice here is I go from green directly into this blue. And then when I get out of the green, I'm going from green to brown. So you can almost see right here where this flat line is, the evidence of maybe a flat spot in here showing you the edges of the reservoir. Now, curiously enough, I had that same pattern over here on the side, but I have no well going through it, so I don't know if that's good or not. But I have none of that green above the Chris R in my client's block. If you look at that neuron that represents that infiltration of the line, you can see the aerial extent of the reservoir from which this well is producing right here. Here's my recipe. I used the far angle stacks to create my attributes, and I used the first three attributes out of the first three eigenvectors. So this is what I came up with for a recipe. Now, in the last slide, we saw that one area off to the down dip, and I think this is an extension of a little channel that's coming through here, but separated from the main field. And if that's the case, this is probably productive down here. You just have to bite your lip if you want to drill down dip from known production. So obviously, I told my client, don't waste your money. I don't think you're going to have a reservoir there, and they were happy with that. Saved them a bunch of money and heartache. So the second example of when not to drill a well is actually in a carbonate, and it's in a West Texas reef in the Pennsylvanian. So a gentleman had come to my client with a prospect that he was interested in, and my client drills wells out in this part of the country, so he was kind of interested in it, but he wanted me to run it through Paradise first, just to make sure it was going to be economic to drill. Now I have a field over here which has produced 1.5 million barrels of oil and a little bit over a half a BCF of gas. And then I have a show well that's made a little over 2,900 barrels right here. Now, if you look at the reef map, here's the old field. The prospect was this whole area right here. And the gentleman who was selling the prospect said, well, no, it won't be 1.5 million barrels, but it's probably 300,000 barrels, which in this area at the time was economic to drill. And I turned off all the shallow wells. There's a whole bunch of San Andreas production here, but I've turned off everything except those wells which are deep enough to penetrate the Penn Reef. So what I did is I mapped below the reef, and I mapped so that I could do my analysis between horizons. In Paradise, you can have it run a neural analysis above and below horizon, between two horizons. You can do it on a time basis, but I use horizons a lot because I'm really focused on one zone or another. And if you look at the regular seismic data, this is the lower horizon that I mapped, calling that the base reef. And then here's the upper reef. Now it looks like there's two reefs here, but my arbitrary is actually going in and out of the plane of the reef. So it's all one reef. And you can see the zones that were perforated. Well, here's my show well. Then here's the prospect area. And again, the gentleman who was showing that said all this is connected and there's 300,000 barrels of oil in there. Well, after I ran my analysis, and here again, I'm using things like relative acoustic impedance, because in carbonates, it's really good for looking for porosity. I'm using thin bed and instantaneous frequency, because I know that the porosity streaks are generally pretty thin. But actually, after you see the results of it, you can map the true base of reef, being this lower green section of neurons right here. You can very easily see the top of the reef itself, and I did go back in and adjust my mapping after I got this analysis out. But more importantly, you can see this color, this red and yellow and oranges in here, which represent the porosity in the reef proper and from where the production was coming. And the reason why you see so many different colors in here is that you might be looking at porosities that range in the 6 to 15% range. You could be looking at different permeabilities. Each one of these little voxels is representing a very specific rock type and has very specific rock properties. So sometimes your whole production zone could be made up of several different neurons. Over here in the prospect area, I'm not seeing a whole lot of that, but I'm seeing some. And at the show well, I'm seeing virtually nothing. So when you take it and look at it in the 3D viewer and you turn everything off, except those patterns which are pertinent to the production or the porosity, you can see a very well-defined reef over here and the wells which produce from it. What's unfortunate, however, is that the prospect area does not seem to be attached to the little zone where we have the show well. And so I took that and put it on a map and planimetered it. And the field that made 1.5 million barrels, not only was it 133 acres, but one of the wells had 150 feet of porosity in it. At best, I have about 30 or 40 feet here, but this is only 7.6 acres. And then the show well itself was on 4.2 acres. Now, 7.6 acres with 40 feet of porosity is not going to give you 300,000 barrels of oil. And it takes about 150,000 for this to be economic. So I was able to go back to my client and say, no, let's avoid the risk, let's avoid a sub-economic well and walk away from the prospect, which he did. Now, in carbonates, finding hydrocarbons is a little bit more challenging because you can't tell if it's fracture porosity, if it's primary porosity. Usually the porosity is very thin. So there's several challenges that are going on. And this is a millisecond, so that I could literally go to a half millisecond. We have found that you can kind of downsample or to half the sample rate without inducing a lot of noise or artificial information. And so with this 1 millisecond data, I went to a half millisecond because I knew I was dealing with a carbonate, which is really fast, and looking for thin porosity. Now, on top of shooting a really good 3D, they had drilled 4 pilot holes and 2 horizontals without finding barely a whiff of oil. And the whole thing was shot on the premise that there's 3 wells up here that made 158,000 barrels of oil, one of which made 128 by itself. And the preconceived notion was this was a fracture play. So all they had to do is come down in front of these big fault systems and drill wells and pick up the fractures in the oil. Well, again, 4 straight holes and 2 horizontals later, they hadn't found any economic reserves. So they were beginning to scratch their heads. And excuse me a second. And so they came to me and said, what's going on? And I looked at the data and I pulled together at the best well. And I saw the effect of what I was seeing at the time, AVO effect. In a carbonate, you're looking at peak changes with offset. In a classic, you're usually looking at a type 2P or type 3 with changes in the trough. Now, I talked to Rocky Roden, one of my co-conspirators at Paradise with me, and rather than looking at this as maybe a result of residual hydrocarbons, we thought that this might be an indication of porosity. So using that, I took the far offset stacks or the far angle stacks and ran my attributes on those. And here is my recipe. The AVO stack, I always use a stack from Gathers if I'm going to use angle stacks from 30 to 38 degrees at a half millisecond sample rate. Relative acoustic impedance. The envelope bands on envelope breaks and envelope bands on phase breaks are two attributes in Paradise that are very similar to average energy and paraphase in Kingdom. I created a far minus near times far volume to accentuate any AVO effect, helping me find porosity. I used instantaneous frequency because I knew I was dealing with thin beds, and then I used sweetness. And what I found is I found a pattern or a neuron that exactly tied the perforated interval in 2 out of the 3 wells. I don't have the other one in the arbitrary. It actually tied all 3 wells. Now here, I only have 24 feet of perforations, but that's only 4 samples, just because of the velocity of the carbonate and the Austin chalk. Here, you can see that I've got, this is just a blow up of this area right here. So I'm looking at the stack and I'm seeing my primary pattern, which tied the perforations, but then I'm seeing this red stuff underneath it. And this is the stack I'm looking for, because again, hydrocarbons do affect the rock properties above and below when it comes to seismic response. So you're always not just looking for what ties the perforations, but the response to the rock above and below it. And when I look at that in the 3D viewer, I'm saying, okay, well, here's my primary. This was the equivalent of the yellow. And all these greens would be the equivalent of the reds in the Kingdom version. And see the distribution. Well, rather than looking like fractures along these faults, it seemed to me that this primary looked more like a channel system. And I went back to my client and I said, you know, I really think this is more channely than it is fractures. And the sand that was producing in these 3 wells was at the very, very top of the Austin chalk, which is a known major unconformity. So again, I'm going to look at low probability to see if I can see the changes. And when I went to the low probability, so these are all the anomalous data points that are left behind when I turn all the background noise off. And lo and behold, my production goes away. Here it is with all the data points turned on. And here I am in the lower 10% of the anomalous data points. So here the low probability is showing me the depleted zone. This is no longer anomalous, but all these areas are still anomalous, which means they probably still have hydrocarbons in them. And to show my client that was probably more of a channel play than a fracture play, here's the little thin sand, which has produced that 158,000 barrels of oil. It's at the very top of the chalk. When the chalk was subaerially exposed and eroded, you can see evidence of these channels that were eroded down into the chalk. And it's this little carboniferous channel sand right here that holds the key to the production. So you can see evidence, if you stare at this long enough like I have, you can start to see all these little channels and wormholes in the top of the Austin chalk. So sometimes you have to think about your preconceived concepts and be prepared to have Mother Nature show you something different when you get into the subsurface. Now this is a quick example of what we can do with unconventional work. And this work was actually a study done by Patricia Santacroce in the Eagleford for a client. And as long as I've been interpreting data, which is, you know, I've been 44 years plus, I've always wanted to get my seismic information at the same scale as my log information. And in this area, the Austin chalk is a peak event, and the Buddha below the Eagleford is also a peak event. So we're looking at 30 milliseconds of trough. And in the wavelet world, you would just see the trough. But in the classification world, you can actually split the Eagleford into 6 different facies. And better than that, you can start tying those facies to your well logs like Patricia did, looking at the top of the Eagleford, the N55, neuron number 55, and this sweet zone. This is a target zone. This is the highly resistive zone. This is the best TOC. Now we can track that sucker, and we can tell by looking at the wells how well they stayed in zone, if they porpoise in and out, or in the next case, where we've taken those neurons and isolated them to show where some of the wells missed them completely, and some of the wells were above it or below it. So she was able to go back and calibrate 170 wells, cores, production, the whole 9 yards, in this study, which was a beautiful study. Now, lastly, one of the things I'm getting into is while I'm drilling wells and I've run my SOMs, I'm trying to work with the mudloggers to help me determine the lithology as I'm drilling these wells. And so here's a case in the Delaware Basin of southeastern New Mexico, where I'm drilling a well, and you can see the spot of where we were. And I've looked at this area right here, and I have gone through an 80-foot thick kind of combination dolomite and lime zone. Now, the upper 40 feet, if you can look at the mud log right here, the upper 40 feet of that zone is very heavily fossiliferous. And that ties perfectly to this blue zone right here. And the minute I get out of that heavily fossiliferous zone, and I'm into a combination of limes and dolomites, I switch patterns. So this is the subtlety to which these patterns respond to changes in rock properties in the subsurface. When you can start getting down to heavily fossiliferous versus non-fossiliferous. And in fact, here I've got dolomite changing to limestone, and you can see the patterns change right here. So this is how closely we can map the subsurface, even while we're drilling wells. Another well I was drilling, I'm looking at a lot of changes in patterns right here. Specifically, I'm looking for a chert, which is kind of my seal or my cap to hydrocarbons in this area. But then I start kind of going crazy, and people go, well, how do you interpret that? Well, look at the mud log. Here's my chert layer, but I've also got lime, I've got chalk, I've got 2 different kinds of clays and shales, I've got plastics, and I go back into lime again. So Mother Nature is not ever simple either. And you just have to be able to understand that these patterns are giving you clues into quickly changing rock properties in the subsurface. With that, I'll stop. And my summary and conclusion is that I have been able to use the classification, the sample statistics, to help my clients find oil and gas for the last 8 years. It is not one and done. You have to keep on playing with it. You have to make substitutions in your recipe until you can tie your well and get a good understanding of what's going on. Understanding geology and looking for depositional forms to interpret the patterns that you're seeing is very helpful. And then also what's important is understanding the attributes, and what the attributes are designed to discern and pull out information in the seismic data is very important, and it is actually the key to success. And with that, I'd say if you want to go and learn more about what we're doing, go to www.geoinsights.com, and after this presentation, I'll take any questions if I can hear them or type them. And I'll go into the chat room afterwards and help anybody out if I can. Thank you very much. I'll turn it back over to Laura.
Thank you, Deb. I know you can't hear me right now, but the rest of you should be able to. As she said, you're welcome to type your questions into the chat, and she can answer them just now. Alternatively, I believe after this presentation, she's going over to our Meet the Experts page, where we have different rooms set up, and she'll be in the geoscience application room if you'd like to ask her questions directly here after this meeting. We'll hang on just a couple of minutes and give people an opportunity to put in their questions.
Okay, I'm gonna go to the chat room, guys.
All right, thank you very much, Deb. We'll see you later. Hello, good afternoon, ladies and gentlemen, and those of you watching on Teams and on our YouTube live stream. We're so glad you could make it. We have a great presentation today from Rocky Roden called What Interpreters Should Know About Machine Learning. If you have any questions during the presentation, you can put them in the chat box if you're on Teams or in the comment field if you're on YouTube, and he'll be able to answer those just verbally at the end. So without further ado, here's Rocky.
Machine learning. My name is Rocky Roden. I hope all of you listening out there are safe and well, and maybe this presentation will help you get through these trying times. This presentation will be given from an interpreter's perspective, from my perspective. A lot of the questions that I had through the years as it relates to machine learning and kind of where things are going now and in the not too distant future. The course outline for this presentation is why machine learning now? Why is it of significance now to the interpretation community? We're going to address some of the terminology confusion as we go through this presentation. We're going to go over the different types of machine learning, case studies related to these different types of machine learning, the black box connotation that's kind of given to machine learning because it is a black box in many cases, and the computer power that kind of evolves in the need when we're applying machine learning, and of course future trends. Where are we going with all this technology? We hear a lot of words today in our lives related to machine learning, artificial intelligence, deep learning. It can be quite confusing at times. But the focus of this webinar is how does all this technology relate to finding oil and gas? So why use machine learning now? Well, machine learning is very good at helping to analyze large amounts of data simultaneously. It's the big data issue. Machine learning can certainly help us determine the relationships between several types of data all at once. For example, in the interpretation process, we typically look at 2D cross plots, 3D cross plots. But what happens if I have 5, 10, 20 different types of data? How do they relate or not relate to each other? Machine learning can help us in this regard. Machine learning can also help identify nonlinearities in a lot of the solutions that we use now in our interpretation process. We quite often make assumptions on different elements of the Earth when in reality they're not linear, they're very complicated. Quite often machine learning can help understand these nonlinearities. It can certainly help improve the efficiency and accuracy over time. And ultimately, it can help automate a lot of these interpretive processes to help us get more effective and more efficient. And of course, the ultimate goal in applying machine learning is to help interpreters reveal geological features, properties, or trends that are very difficult to see in our data, or difficult to interpret, or elements that we don't even see in the data with conventional approaches. Ultimately, it's reducing the risk in drilling for oil and gas. The challenges and opportunities for machine learning in the geosciences. Geoscience is deeply grounded in physical laws and principles. These have been developed by many of the people you see pictured on the right there over multiple centuries of a lot of systematic research. Geoscience features have space and time relationships, highly multivariate. They follow a lot of nonlinear trends, as I mentioned previously, a lot of non-stationary characteristics, and often they involve rare but significant events. And then our geoscience data itself can have challenges, multiple resolutions, varying degrees of noise, incompleteness, sample size issues, and improperly processed data, just to name a few. So the questions then is how can geoscience interpreters ensure that the established physical bounds and rigorous theories that we have established over centuries are not violated by machine learning? And by the same token, how can we advance our geoscience interpretation, especially with machine learning, if we were restricted by the established practices of the past? Well, the answer is actually pretty easy, or the proof of it is pretty easy. In the oil and gas industry, the proof is what is found by the drill bit. That ultimately tells us the answers. And it's obvious we don't have all the answers yet. If we did, we would never drill a dry hole. Forbes indicates that data is growing so fast that by this year, 2020, data will be growing at the rate of 1.7 megabytes per second for every person on Earth. Tremendous amount of information. That's why the data science field has grown dramatically over the last decade. And data science really just encompasses anything related to preparing, looking at, analyzing the data, lots of data. And of course, the big data issue relates to having such massive amounts of data that we have to have some other processes to evaluate it. Traditional database and software techniques don't work anymore. And of course, data analytics are just the approaches and the techniques we use to analyze all of this information. The question is, what is machine learning? Most people give the definition of machine learning and credit it to Arthur Samuel, who indicated that it's the field of study that gives computers the ability to learn without being explicitly programmed. We've heard a lot of the modern day challenges of our computer systems beating the chess champions of the world and some of these other games. But a lot of people don't realize that Arthur Samuel developed a IBM machine that ran machine learning to beat the checker champion of Connecticut. I don't know how many people play checkers in Connecticut, but he did beat him. So you see the initial evolution, or some of the initial evolution of machine learning. In this display, you see a lot of the different sorts of categories of data science. But what's important to look at is where machine learning is sitting in this mix of different data types or different sorts of data science categories. As you can see, it's part of AI, or artificial intelligence. Well, artificial intelligence is a big, very significant category of data science, and it's any technique that enables computers to mimic human behavior. A subset of artificial intelligence is machine learning. Machine learning, as we just described from Arthur Samuel, it's a technique that gives computers the ability to learn without being explicitly programmed. And a subset of machine learning is deep learning. And that relates to the computation of multi-layer neural networks. And I'll talk about that again in just a minute. Now, if you were to Google machine learning, you'll get something like this: supervised learning. Supervised learning is the most widely used type of machine learning. And it takes a known set of input data and the known responses to that data. In other words, I know the answer to something, and I take the descriptions or labels that describe that. I develop a model to find the answer that I already know. And then once I've developed that model, I can take that, apply it to another data set, hoping to find what I found when I developed the model in the first place. Unsupervised learning is actually quite different. In unsupervised learning, there is no knowledge of the data previously. The training adapts to the data, it looks at the data, identifies natural patterns, structures, and clusters. To give you an example, most researchers think that babies, when they're born, up until they're about 9 months to a year old, fundamentally learn by unsupervised learning. They come into this world not knowing anything. All they know are the items around them, their surroundings, their parents. That's all they see. They look at the relationships of the things around them. Very good example of unsupervised learning. Semi-supervised learning really is combining both supervised and unsupervised learning in different ways to get better answers. And then reinforcement learning is a type of algorithm that learns over time, and it maximizes returns based on the rewards it receives from performing certain actions. Now, what I'm going to go over is supervised and unsupervised learning and how it's being used in a few examples of interpreting geology. We'll talk about semi-supervised and reinforcement learning later in the presentation. There are many types of supervised learning and unsupervised learning. I've listed here are some of the different sorts of these machine learning approaches that are seen and used in the geoscience community in interpretation. If you'll look on the left, there's a list of supervised learning approaches. There are certainly more than this, but these are the ones, again, that are most common or very common in geological applications. The ones you see in red relate to non-neural network statistical approaches. And of course, there are neural networks under supervised learning. Over in unsupervised learning, we have neural networks again, different than in supervised. And we also have something called dimensionality reduction. And I'll talk about that as it relates to unsupervised learning shortly. Now, these non-neural network supervised learning approaches like linear regression, decision trees, random forests, these are all regression and classification approaches used to help make or help solve some interpretation problems. And I'm going to give you some examples. Being an AVO guy, one of the things that I've been doing for years, and anybody that interprets AVO is familiar with, is calculating intercept and gradient. It's a very simple linear regression when I'm calculating how amplitudes change with offset, depending on what kind of linear approximation I'm using. For example, here's a Shuey 2 term. I cross plot that, I do a least squares linear fit. The slope of that line is a gradient, the intercept is a zero offset. Those are two of the fundamental AVO attributes used in our industry. Linear regression, very simple, very straightforward. Another approach of non-neural network in supervised learning was by ConocoPhillips. They did an analysis of their 40 surveys in the Gulf of Mexico and the North Sea, and they came to the conclusion that the inversion, acoustic impedance inversion they were using was not sufficient enough to see the changes in the reservoir properties that they wanted to see. So as a consequence, they applied random forest and gradient boosting, along with 40 seismic attributes and pre-stack data, and it apparently enabled them to much better predict the change in pressure, the change in water saturation, change in gas saturation. Again, using some non-neural network supervised learning approaches. But neural networks are obviously a very popular and common approach of machine learning used in interpreting geology and geophysics. And a lot of the neural networks are based on the biological neural network, which relates to the brain, which is a collection of 10 billion interconnected neurons, and each of these cells uses biochemical reactions to receive, process, and transmit information. Now, an artificial neural network is nothing but a computational simulation of that biological neural network. It's composed of a large number of highly interconnected processing elements called neurons. As you can see here, we have both supervised and unsupervised, and there are neurons in both of those, but they're used very differently. The computations are very different. So I have a test here. You're sitting at home, and here's a test for you. Look at these series of numbers, and based on that, tell me what the answer is at the question mark. Hopefully you got 81. Congratulations, you have successfully accomplished supervised learning. You looked at the series of numbers, you built a model that relates to squaring the first number to get the number on the right, applied that to the test at the bottom, and got 81. This is a very typical example of supervised learning. And how supervised learning works is I take a known object, for example, here a cat. It's my cat. And I have a description of it, which are sometimes called labels. Paws, a tail, a nose. And ultimately, I develop a model that says, all right, with this description of this cat, I can determine it is a known cat. I take that model that I have developed, apply it to another object, apply the model, and it tells me whether I have a cat or not. This is fundamentally supervised learning. So what are the pros and cons of supervised learning? Well, one, it's a very clear objective. That's why it's used a lot, and it's the most used machine learning application basically in the world today. It's easy to measure the accuracy, and it's very controlled. The cons are that it can be labor intensive, especially if you're trying to develop the labels or descriptors. Do you have enough information to really do that, to really build an accurate model? And it fundamentally does give you limited insights because you're telling it what to find. It's not going to find anything that you don't tell it to find. Another aspect of supervised learning is in the neural network. If you look to the left there, this is a very simple neural network, sometimes called a shallow neural network. You have the input, which are the descriptors or labels. You have one hidden layer of neurons, and then you have the output. But if you look on the right, this is a deep neural network, sometimes called deep learning. There are several hidden layers there, and in this case, a lot of neurons in each one of those layers. Now, the most popular deep learning approach today is on the bottom, as you see in that display, is a convolutional neural networks. Now, convolutional neural networks were developed out of an image recognition, and it takes an image input and assigns weights and biases to differentiate one from the other. That is convolutional neural network, a type of deep learning. So now let's go over a supervised learning case study. This is going to be a deep learning approach using convolutional neural networks. In this example, I've got a seismic line, and I am going to identify seismic facies. So what I do is I look on this seismic line. Actually, I typically will look at several lines in a 3D survey. I will identify reflection patterns on those lines that I want to be interpreted throughout the whole data set. So I identify these patterns. It starts to build a model that recognizes these different reflection patterns, hopefully in many cases associated with seismic facies. Typically, these are generated or run on graphic processing units, which I'll describe shortly. And it looks at the data, takes this model, analyzes all the data based on the few input lines that you gave it to build the model, and then it classifies the whole data set. And once it's done, then you have a three-dimensional result of the facies that you initially wanted to see in your data. This is an example of a convolutional neural network for seismic facies interpretation. Here is another test. How many patterns or clusters can you identify from these 6 objects? Look at these and think about that. How can you group these 6 objects? Well, one is shapes, round versus a box. Another is fruit or non-fruit. Another is color. You could say there could be another one as it relates to peeking in the top of the box or peeking in the top of the fruit. But regardless, if you've found these different categories or different patterns, congratulations, you have successfully accomplished unsupervised learning. Very different. You're looking for the natural patterns or clusters in the data that you were given. So how does unsupervised learning work? Well, I have a lot of data, my raw data. I know nothing about this data. I apply an unsupervised learning algorithm. It examines the data. It learns from the data. It identifies patterns and clusters or classes, if you will, in the data. And then it separates that out into these different patterns. Now, what's different about unsupervised learning is you have to interpret those patterns. It's not like supervised learning where I knew what I was trying to find. You may or may not understand what you ultimately get out of unsupervised learning. So what are the pros and cons of unsupervised learning? First of all, on the pros, it's very fast to start. I don't have to have a lot of descriptions or labels going into this process. It can be very disruptive. It may show you things you never saw before. It may show you some things you didn't understand. Now, the cons are it's somewhat difficult to measure the accuracy. It does require a little bit more experience on the parameters quite often. And there's another issue called the curse of dimensionality, which I will go over. The curse of dimensionality is a phenomena that's quite often associated with unsupervised learning. So what do I mean by that? Well, it refers to a phenomenon that occurs when you're analyzing several different types of data. In other words, several dimensions at one time. And there are issues that come up that aren't related to our normal 3D world that we live in. In other words, as the amount of data or dimensionality increases, the volume of space increases so fast that the available data becomes sparse. So what do I mean by that? Well, take, for example, the 1D plot you see on the bottom there. You see a series of data points on that 1D graph. If you take those same data points and put it in a 2D cross plot, you see you start to spread the space out in between these data points. If you take it into the 3D grid on the right there, you have a lot more space between these data points. So as the number of data types or dimensions grows, the amount of data required to analyze it accurately grows exponentially. Because if I'm examining 10, 15, 20 different types of data, I'm in 10, 15, 20 dimensions, and it requires a tremendous amount of data to really analyze it. So how do we deal with this? How do we defeat the curse of dimensionality? Well, one is by incorporating prior knowledge. And we need to reduce this dimensionality because, first of all, we have to do it to improve the classification performance and to make these interpretations even feasible. So what it does, what we need to do is to reduce the dimensions you're looking at to the part of the data space where your data is most dense, fundamentally ignoring the parts where the data is sparse. One of the most common and popular approaches that we use today to reduce dimensionality is principal component analysis. Principal component analysis is a linear mathematical technique to reduce a large set of variables, for example, seismic attributes, to a small set that still contains most of the variation of independent information in the large set. So what does that mean? Well, what that means is it can help us find, if I have a bunch of seismic attributes, it can help us find what are the most prominent attributes in the data set that I have. Here's a graphic approach to understanding principal component analysis. If I was to cross plot a couple of attributes and the data points looked as you see here on this 2D cross plot, what is the largest variation in this data? Well, as you can see, the largest spread or variance in the data is by that red line. That is the first principal component. What is the second largest variation in the data? I have two attributes. I have two principal components. The second one is orthogonal to the first, but it shows the second largest variation in the data, which is that green line. That's the second principal component. The eigenvector is the direction of those principal components, and the eigenvalue is actually the measure of that variance. So how does that relate to us as interpreters? Here's an example of principal component analysis. Here we have taken 12 seismic attributes and run PCA. And what you are looking at there in those blue bars is the highest eigenvalue on each of the inlines in this 3D survey. So for example, if I took that red bar and wanted to look at the principal component analysis as it related to that red bar, say that line was running right through a well of interest to me, then I get the results. I have 12 attributes, I have 12 principal components. The first principal component, which is the highest eigenvalue, which you see there, the listing of the attributes to the right, there's 12 of them, and their percentage contribution is highlighted there. As you can see, there are 4 attributes that stand out over 90% contribution in that first principal component. There is no question those 4 attributes are very prominent in the data. Now, if I look at the second principal component, you can see these 3 attributes are very prominent in the data. So in looking at the first and the second principal components, there are 7 attributes that are very prominent in this data set. And then we can take those 7 attributes and take those into an unsupervised approach like self-organizing maps. Now, the key issue here is there's no question that those attributes are very prominent. The real issue is, are they the attributes that really bring out the identification of the geological features I'm looking for? So self-organizing maps, remember, is an unsupervised learning approach. And it classifies data into categories, clusters, or patterns based on their properties. And a neuron is nothing more than a point that identifies one of these natural clusters or patterns in the data. Some of these clusters are going to have geologic significance. Some of them will not. It will identify noise, coherent noise, incoherent noise. It may identify elements in your data that you don't even care about. But some of those clusters are going to have significance as long as we pick the right set of attributes within the realm of reasonable good data. So how does this work? Well, actually, it's not too difficult, really. But if I had a data set, for example, and I want to analyze a very specific zone of interest, I've identified this zone of interest either between a couple of times or depths in my data, above or below a horizon, as I have here, between two horizons, whatever my interval of interest is, I identify that. And if I've gone through and I've run principal component analysis and I've identified there are 10 prominent attributes in this data set, in this zone of interest that I'm looking at, what I do is I take every one of these 10 attributes in that zone of interest, which means every single data point in that zone of interest has 10 values because I have 10 attributes. I take all of those data points and I take that into something called attribute space. Initially, I was in survey space, but now I've calculated these attributes. I'm taking all these data points. I put them in something called attribute space, sometimes called hyperspace. Because I have 10 attributes, I have 10 dimensions. I can't see that visually because I have 10 different data types. The first thing I do is take all those data types and I normalize them or standardize them to the same scale. And then once I've done that, I will place neurons, and in this case, I'm going to place 64 neurons randomly in this attribute space. And then I tell the self-organizing map algorithm, find the patterns in the data. The data points never move. The neurons move around with some actually very simple math until it's identified, in this case, 64 neurons or patterns in the data. And once it's done that, it non-linearly maps this back to a neuron topology space. In other words, if you're looking at this 2D color map here, there are 64 hexagons. Each one of those represents a neuron. Each one of those represents a pattern in that data that contains different percentages of those 10 attributes that went into it in the first place. And this is how we take this information through the SOM classification process and go back to survey space. Now, each one of those neurons identified by color shows up in the 3D survey space so I can make interpretations. I can turn any one or sets of neurons on or off to see whatever geology those particular neurons bring out in the data. So let me go through and give a case study, an unsupervised learning case study using principal component analysis and self-organizing maps. This is in the offshore Gulf of Mexico, a very simple class 3 AVO bright spot setting. We're looking at a relatively shallow reservoir. You're looking for amplitudes. I'm looking for something that relates to DHIs perhaps that can reduce the risk in drilling these prospects in this area. Now, before these 2 wells were drilled, there were 7 wells drilled in this area, all of them on amplitudes. They were all wet or low saturation gas. Before these 2 wells made discoveries. I took this data in a zone of interest. I took 20 instantaneous attributes into principal component analysis to find out what were the prominent attributes. Now, after taking these 20 seismic attributes and running through principal component analysis, you can see the results. Again, across the top, you see these bars that represent the highest eigenvalue and each of the inlines in this particular survey. Now, I've selected an area, which are where the red bars are located, and the PCA results below are the average over each of those bars in total, the red bars. And so what I have looked at is the first principal component, second, the third, and the fourth principal component. And then I look specifically at the highest contributing attributes in each of those four principal components. And the highest percentage attributes as a whole came out to be these 8 attributes. So these are the 8 attributes that I took into self-organizing maps. On this display, what you're looking at in the top display is a map of the amplitude, the top of the reservoir. It's a very prominent, very high amplitude event. And as you can see, you got a very good amplitude conformance to structure. It's relatively consistent within the mapped target area. But what you're looking at on the bottom there is actually a result from the self-organizing map analysis. And what you're looking at there is low probability in white. And what low probability is it's a measure of the probability of the data points and how close they are to the neuron that identified that particular cluster or pattern that they're in. For example, if I have a neuron with that has identified a set of data points, a cluster or a pattern, all the points that are very close to the neuron have a high probability, but the points that are very far away have a very low probability. They're anomalous. Well, what is anomalous in our seismic data? Well, one of them are DHIs, direct hydrocarbon indicators, by definition are called seismic anomalies. And what we have found is quite often these low probability anomalies from the SOM analysis relate to direct hydrocarbon indicators, depending on what the geological setting that you're in, and of course the attributes you're using. So as you can see by these, comparing these two displays, the low probability, in this case less than 1% probability, was very clearly defining the lateral extent of that reservoir. But if you look at it from the standpoint of analyzing the neurons on the patterns that they specifically see, this is the result. What you're looking at here is an inline right through the middle of this field. That top display is an amplitude, typical conventional amplitude line in time through that field. The SOM results are the bottom two displays below there. And if you look at the field defined by this display, and if you go to the middle display there where the SOM was run, there are 25 neurons were used here. And the 20th and 25th neuron is identified in gray. And if you look on that seismic line, that gray represents that reservoir above the hydrocarbon contacts. And the hydrocarbon contacts were identified by that reddish color, neuron number 15. It identified a gas oil contact, it identified an oil water contact, and it certainly identified something anomalous down dip that has not been drilled yet. Now, if you look on the display on the bottom there, what you're looking at is only those 3 neurons turned on. Now, if you look at the dashed box on each of these displays, what you're looking at is where this reservoir transitions from the hydrocarbon leg into a water leg. You can see what it looks like on the stack data, but if you look at the SOM analysis, you can certainly see we're getting down to 1 or 2 samples where that reservoir pinches out and goes into the water leg. Much higher resolution than we normally see in our seismic data. This is the same sort of a display, but now you're looking at the strike line through that field. Again, look at the SOM results. You can see that reservoir identified by the 2 neurons in gray. You can see the gas oil and the oil water contact identified by that reddish neuron. Very, very good at identifying DHI characteristics in this particular data set. Now, machine learning, whether you're using supervised or unsupervised methods, is actually relatively simple and straightforward. In fact, many of the very complicated mathematical derivations we use, a lot of them we use in processing, they're very complicated. They're quite involved. They're much more complicated mathematically than a lot of the neural network approaches used in machine learning. But the difference is there are thousands to millions of computations that are involved in these neural networks. And it's this inability to examine each of these iterations that projects the black box perception or connotation. And it is a black box. We have data that goes in, it does an analysis, we get data that comes out with the answer. We don't know, it's very, very difficult for us to understand how it got to that answer because of so many computations. And of course, for seismic data, coherent noise, incoherent noise, insufficient amount of data, there's all kinds of issues with our data that can complicate this issue. But it's this black box phenomena at times that has prevented people from accepting some of the results. But the computations at times can be quite compelling. In fact, in machine learning networks, we typically are trying to mimic human behavior by using inputs and receiving outputs. But think about it from the perspective of a machine learning system. The human's the black box. How do they come up with those answers? But they did. Now, in machine learning, and especially with neural networks, computer power comes in to be a factor. And typically, with machine learning, there are based around issues like CPU versus GPU, high performance computing systems in the cloud. CPUs, which we all know are in essentially all of our computers, and they're very good at executing a few complex operations very efficiently. And obviously, we have these in almost all of our computers today. Now, while a CPU is very good at handling these very complex instructions, a GPU, or graphics processing unit, is very good at handling many sets of very simple instructions. Of course, it evolved out of the video game industry, and it is absolutely the preferred approach, as I showed earlier, using deep learning convolutional neural networks. So which should you use for machine learning? Well, GPUs are typically much faster than CPUs for neural networks. But GPUs cost more money. It really depends. It depends on the economics, the time, the size of the job, the type of machine learning. All must be considered, and quite often, whatever machine learning application you're using, it is already written for a GPU or a CPU. Now, the other sort of way that machine learning is computed is in high-performance computing systems, sometimes called supercomputers. And these high-performance clusters consist of hundreds to thousands of compute servers that are networked together. And typically, they are clustered in parallel with each other, and this boosts the processing speed to give you a lot of high-performance computing. Of course, this is at a price. Now, the cloud refers to these servers that are accessed over the internet and the software and databases that run on those servers. That could be a high-performance computing system. It could be just a server that you're doing your machine learning on. Whatever it is, you can have that into the cloud. And cloud servers are located in data centers around the world. And it allows companies and users to not have to manage physical servers themselves or to run software applications in their own internal machines. Now, all of this comes at a price, which always comes in, obviously, into what you use from a computer standpoint and how you use that in relation to machine learning. Now, the majority of the machine learning approaches today have been applied to our established geoscience workflows and practices. In other words, we are trying to improve elements of our traditional workflows. So the question is, can machine learning discover something profound that we have not seen before? So what do I mean by this? Something profound. Well, there was a study done at the University of Ontario where they were looking at premature babies in a neonatal intensive care unit. And they put a set of telemetry devices on these babies. And the purpose of this was to try to accurately identify when these babies were starting to develop infections, the biggest worry for premature babies. But when they did that, this information went into a machine learning algorithm. And what they started seeing was they were identifying up to 48 hours symptoms before 48 hours before any of the symptoms were evident on these babies that they were going to have infections. And this process was starting to be so good at identifying this that the doctors and the clinicians started to believe what they were seeing because it was almost always accurate. They could not explain why this was giving them these answers before they could see any symptoms. Of course, there's a scientific explanation for that, but they didn't know what that was. And it proved itself over and over. This is profound. This found something they did not know before, and it gave them some answers they never knew before. So with these different sorts of machine learning, which one of these might provide one of these profound step changes in how we do interpretation? Well, I've talked about supervised and unsupervised learning. And supervised learning certainly is the most prominent sort of application of machine learning used in our industry. Unsupervised learning is less used, but unsupervised learning might provide us with one of these profound step changes because it can produce disruptive changes that we've never seen before, unlike supervised where I'm telling it what to find. But in reality, probably the biggest advances in our interpretation is probably going to be in the semi-supervised and reinforcement learning approaches. Here's an example of a semi-supervised learning, which really is combining both supervised and unsupervised learning approaches. For example, if I have going through a unsupervised learning methodology, I've identified a set of attributes that are really good for faults. For example, coherency, curvature, various types of attributes that see faults or identify faults very clearly. I take those attributes, I run a self-organizing map, which is an unsupervised approach, and with that output from the SOM results, I take it into a convolutional neural network that identifies faults. This is another deep learning approach. I have used two different sorts of machine learning approaches with better data going in than conventional amplitude data, hopefully, to identify faults. This is a semi-supervised learning approach. So will machine learning really change how we do interpretation? Well, if machine learning improves our existing interpretation workflows by giving us answers faster and more accurately, that by itself is significant. And in my mind, that's not only, it's necessary. We have to have that. We have to do things more efficiently and faster with fewer people. Now, what you're looking at here are a set of different interpretation approaches where machine learning has been used. And over the last 2 years, and going to many, many workshops, many sessions, work sessions, in several different conventions, and researching what's been published in the literature, these I found were the most common applications of machine learning for interpretation. Most of these are supervised approaches. A couple of them are unsupervised. Again, these are today I have found to be the most common approaches. There are many more, don't get me wrong. And in fact, there are many used in processing at seismic processing, but these are fundamentally for interpretation. So we are already starting to see machine learning applications provide higher seismic resolution, whether it's supervised learning or unsupervised. We're seeing this in looking at inversion results, fault delineation, stratigraphic facies analysis. We're starting to see the identification of seismic anomalies like I showed you with direct hydrocarbon indicators. We're also seeing the isolation of various types of noise in our data, trying to identify what's real and not real. But as I said before, I think supervised, semi-supervised, and reinforcement learning methods, they hold the great promise. This is where I think everything is going towards. The ability to combine the best of these different machine learning approaches and combining them to get a better answer. I personally think this is extremely exciting. We're in a time where we're starting to have the tools to do this. And I think it's a very exciting future for interpretation, barring the outside issues we have to deal with. So I'd like to make a prediction, given what I've shown you as it relates to what interpreters should know about machine learning. One is machine learning can be disruptive. It can change the way you do things. It can give you different answers, hopefully, that are better and more accurate at times. But I truly believe that artificial intelligence and machine learning will not replace geoscience interpreters. I really believe that. I've been around for a while, and I've seen many technologies evolve. And every time one of these technologies evolve, I hear, well, this is going to eliminate the interpreter. But in reality, it provides more capabilities and more tools for the interpreter to do a better job. However, I do think in the next 5 to 10 years that interpreters who do not use machine learning will be replaced by those who do. Thank you for listening to our webinar. So if there are any questions at this point, I'm ready to address those. Thank you.
Well, thank you very much for that, Rocky. We appreciate it. If you want to go ahead and type your questions in the chat box, Rocky will be happy to answer those. And if you are watching via the YouTube live stream, you can just put them in the comments.
I don't see any questions yet, but
We'll hang on for just a minute more.
I'm ready.
Okay. Okay, well, if there are no questions, then I would encourage all of you to go over to the Meet the Experts page. Also on the microsite, you'll find the same link set that you accessed this presentation for. I think the link directly below live presentation says Meet the Experts. And there we have a couple of chat rooms set up that have our experts standing by to answer your questions or give you a demo or anything like that. So you're welcome to pop by over there. If there's nothing else at this time, we'll go ahead and cut it off. Our next presentation will be at 3 o'clock. Thank you so much for joining us, everyone. I'm sure other people will join us as you get started.
Sounds good.
Hello, ladies and gentlemen. Thank you for joining us today for Carrie's talk on calibrating SOM results to wells, improving stratigraphic resolution in the Niobrara. If you have questions during the presentation, you're welcome to put them in the chat. If you're watching via the YouTube live stream, you can put them in the comments and Carrie can answer those verbally at the end. So without further ado, here you go.
All right, thank you, Laura, and thank you to whoever's in the audience out there for attending my talk today. I'll be presenting a case study for an unconventional reservoir, which illustrates how self-organizing maps can push the limits of seismic resolution to single sample, and how we can take these results and use our well data to validate our machine learning results. An outline of my talk, I'm going to do a little bit of introduction of the promise of machine learning when applied to seismic data, take you through how attributes, sampling, and self-organizing maps combine into a workflow which can help resolve geology below the traditional tuning thickness. And then I'll introduce you to the Niobrara petroleum system, which is where our case study is based. And then the specifics of the multi-attribute machine learning interpretation thought flow, which has two components: principal component analysis followed by unsupervised learning in the form of self-organizing maps. Then we'll go through the results for the Niobrara interval and visualize the SOM classification first, then go through the steps to calibrate those results to well data, and then have a look at the well to SOM statistics and actually how you can choose the best SOM topology based on the extracted data at your well locations. So why should we as geophysicists care about seismic multi-attribute analysis? For years, we've had hundreds of attributes that we can compute from our seismic data for decades. And those are always very loosely tied to the physical conditions of the subsurface. It's always been a challenge to directly tie a single seismic attribute to a specific property of the subsurface, like lithology, pressure, fluids, what kind of fluids, etc. So this has always been a challenge. And over the last few years, because of the increase in computer power, companies have stepped up the investigations into the use of machine learning in a lot of areas of E&P. And for the geosciences, the emphasis has been in reservoir characterization, seismic data processing, and to a lesser extent, interpretation. However, interpretation tools have come on very strongly in 2019 and 2020. You see a lot of papers at the convention this year about machine learning and especially deep learning for things like fault detection and facies detection. Paradise has been available in the interpretation space for many years, and the SOM technology that we apply to our 3D data in this example has been applied to hundreds of data sets over the past 10 years or so. So this is a very mature technology, and it's been proven out by lots and lots of case studies. So it's well vetted. Anyways, back to the motivation for multi-attribute methodology. We're looking to address the task of interpreting dozens of seismic attributes. So it's always been a big data challenge. There's also the inability of humans to visualize attribute relationships beyond 4 dimensions. So in these two examples, we show how we can see attribute relationships, and we can have a 2D cross plot with color. A 3D cross plot with color takes us to 4D, but beyond that, we can't really see the relationships. However, a computer has no such limitations. So computers can easily address relationships between 5, 10, 15 attributes simultaneously. So as I mentioned just a minute ago, we're taking advantage of the improved computer power and visualization technologies. We have things like 2D color maps in Paradise that bring a little bit more to the 3D visualization environment. But ultimately, really what we're trying to get to is better interpretations, more accuracy, a reduction of risk, or more money for your company. Financial success is really what we're driving toward. So let's start with the types of machine learning that you are in common use today. If you were to Google machine learning, this is what you'd likely see in the 4 categories, and we'll take a brief look at each of these. Supervised learning is really probably the most popular method in our industry today, and supervised learning will take known input data and train a model to apply to new data points and predict a result. The advantage of supervised learning is that you get directly to a specific answer, such as a porosity model from pre-stack inversion that's been trained on well data. Unsupervised learning is quite different, but it does have its own advantages. And unsupervised learning has no a priori knowledge of the data. The data is organizing, the data is adapting in training to itself. Sorry, I'm tongue-tied on that one. It finds patterns in data that might not exist in the training data used for supervised learning. And we've seen this time and time again in our unsupervised machine learning projects. And I'm going to look at this a little bit toward the end of the talk as well, where we see results in our wells, but there's actually results in the seismic that we don't sample in the wells. So unsupervised learning will not be restricted that way. Semi-supervised learning is a simple combination of supervised and unsupervised to achieve an interpretation goal. And then reinforcement learning is an algorithm that learns over time to maximize returns based on rewards it receives for performing certain actions. The case study today is going to be focused on an unsupervised learning workflow. So moving on, what we're trying to show today is the ability to improve the discrimination of thin beds using self-organizing maps. Now, a SOM is a method that uses attribute space to classify seismic samples. So in this example, we see a cross plot of just 2 attributes, so it's just a 2D plot. It's actually already classified, so you can see each cluster of samples has been given a symbol that corresponds to the cluster that it's been put into. So some neurons seek out natural clusters in attribute space of like characteristics in the seismic data, and the neurons learn the characteristics of the data cluster through an iterative process. It goes through cooperative learning followed by competitive learning. When the learning is completed, each unique cluster is assigned to a neuron number, and each seismic sample is now classified. You'll also notice that other things that we can measure are the distance from the centroid of each detected cluster. And part of what Paradise also produces is the probability volume that lets you know the confidence that a sample is assigned to the correct cluster. Another important thing that we do in Paradise is we use a sample-based approach to our attributes. So rather than wavelet-based attributes, we're putting in sample-based attributes. And this figure is just simply showing what that looks like for 7 instantaneous attributes that were derived from an amplitude trace. So each of these timing lines through this little time sample is going to have a different value for each attribute, and all of those samples will go into the SOM. Now, I really like this example that shows it's a synthetic model of how a self-organizing map can detect single sample events. So on the left-hand side, we have a model, a synthetic model of RC series, and we have a somewhat thick positive amplitude followed by single sample doublet of a trough peak, followed by a peak trough, followed by a slightly thicker trough. Now this RC series was convolved with a wavelet, And then the resulting trace was duplicated 100 times with added noise. And then simply cross-plotting the real trace and the Hilbert transform, so it's a 2-attribute example, you get this cross plot that you see all the data points plotted in black, and you can see the data is clustering. Now we took that through a SOM process and asked the SOM to classify these 100 traces into 64 classes or 64 neurons, and this is what you can see in this colored plot. And again, you see the clusters have been identified and coded. The color map in this case is just a random 64 colors. Now, when we look back to our seismic events in this classification, we've now numbered the neurons and the corresponding event on the original RC series. And you can see that each event has been distinctly classified. Even these single sample events like the 855 pair has 2 separate classes. The 3328 are 2 different classes, and the other thicker events are also in their own unique class. Now we do have other classes that are just corresponding to other parts of the signal. And part of the interpreter's job is to understand how the classes correspond to the geology in the subsurface. So looking at a more practical example of what a SOM is, imagine that you have, say you have 20 seismic attributes, and through your PCA process, you've identified 10 that you want as input to SOM. So you have your 3D survey space in XY in time or XY in depth. And each sample has a location, and each sample in the survey will have 10 values corresponding to your 10 attributes. In attribute space, that turns into 10-dimensional space. And the SOM process, as we mentioned earlier in the talk, as I mentioned, I should say, within each cluster, we now introduce natural clusters and attribute space. And these are empty initially and named neurons, and they're introduced into the space. You choose what topology. We said 64 here, but you could choose 25, you could choose 144. That's up to the user. And we typically run lots and lots of different topologies. But in this case, we're going to do a 64 pattern SOM. And the SOM process will classify your data in attribute space via the multiple epochs of cooperative and competitive training until each sample is classified and assigned to a neuron. And then these are mapped back into survey space and assigned to a neuron, for which we produce a 2D color map. And once you have this 2D color map, the interpreter can then now query the 3D volume of SOM classification. So each of these neurons represents a cluster of data points, and each data point retains its location in 3D survey space. So now we're going to park that and introduce the area that we're going to present. The Denver-Julesburg Basin is the focus of this study. And you can see the outline of what's called the Wattenberg Field, which is in northern Colorado. And our study area is right up in this area. We had about 100 square miles of data. The Wattenberg is a basin-centered gas field that was producing out of conventional sandstone reservoirs. It's a 70,000 square mile foreland basin covering parts of 4 states, Wyoming, Nebraska, Kansas, and Colorado. The basin has over 47,000 oil and gas wells with a production history that dates back to the 1880s. So it's been in production for well over 100 years, pushing up to 150, good Lord. Anyways, in around 2009, the operators of Wattenberg, who at the time were Noble and Anadarko, and I guess they are now Chevron and Oxy, turned their attention to the Niobrara Formation, which in this cartoon strat column is shown here. And you see typical depths for the various formations. And the target, the Niobrara, is a very rich shale, high TOC shale, so it's a good source rock. And the shales are interbedded with chalk benches, and these are informally termed the A, B, and C benches. So the operators began drilling their horizontal wells starting in around 2009. They quickly were running into issues because they didn't have 3D seismic. So they were crossing faults and drilling out a zone and having a pretty bad time of it. They were also in addition to these 3 targets, they're targeting the Codell sandstone, which is deeper and sits unconformably below the Niobrara. So I'm going to give you a little bit of detail on the Niobrara formation, a little bit more. Late Cretaceous in age and was deposited in the Western Interior Seaway. It's divided into the basal Fort Hayes limestone, which is a dense, very tight limestone, doesn't produce very well. And then it's overlain by what's called the Smoky Hill member, which is where our benches reside. And the units, they're fractured chalk benches and are the primary reservoir interbedded with marls and shales. And then overlying the Codell sandstone, which is also late Cretaceous in age. It's quite heterogeneous. It does tend to thin to the north as you head up toward Wyoming. So when the operators, Noble and Anadarko, one other thing I want to mention quickly is the play expanded in around 2011 when EOG drilled the Jake well, which was outside of the Core Wattenberg field, and showed that the benches would produce oil outside of that Core Wattenberg area. So these 2 developments, the horizontal drilling and the opening of the play, led GPI and Geokinetics at the time to acquire a multi-year multi-client program in northern Colorado. So this is an outline of their multi-client survey. It's about 1,500 square miles. And they provided us with 100 square miles of data in the western part of the survey to run a pilot project to see if Paradise SOMs would improve the resolution of the Niobrara within the survey area. So we had our 100 square miles of data, and then this map to the right shows you we had about 30 wells available to tie into, and these came from the public Colorado Oil and Gas Conservation Commission website. In addition, I've color-coded in red 7 wells that we sent out to have a full petrophysical analysis run so that we had some rock properties to tie into our SOM results. Here's a 2-way time structure in the study area. So you have north on the left, and you can see we're coming up very steeply to the west into a big probably anticline. It looks like a monocline in our survey area, and then down into the basin as we get away from the front range of the Rockies. The inset is from a publication about the Austin Chalk from Friedman, and this is showing structural elements and the types of fractures that you can expect based on the structural elements. And this can be useful to know. The Niobrara these chalk benches don't produce uniformly. They're very dependent on fractures. And so the fracture types you can expect based on the structural element that you're working in is kind of shown here in the inset. What you can see on this 2-way time map is that we have 2 major structural trends. We have a northeast to southwest. You can see faults within the top Niobrara structure, and that's overprinted by a southeast to northwest set of faults. You can also see from the most positive curvature attribute, which this is extracted at the top Niobrara seismic pick, that you do have quite a complex pattern of probably fractures and faults. You can see that again, those main structural trends. And these were computed from the ASPE Consortium Library suite of geometric attributes, which are also available in Paradise. Here's a quick look at the data that we had to work with. The data was very high quality. We have a two-way time on the left in seconds. Our trace spacing is about it is exactly 110 feet, I shouldn't say about. We analyzed 60 milliseconds of data, roughly, and from the top of the Niobrara, which is this very strong, easily picked peak, to the top of the Greenhorn, which is another event that's not too hard to map from the seismic. So within this 60 millisecond window, we have our 4 reservoirs that we're trying to resolve. We have a very high TOC marl, and that is providing this kind of strong, broad trough that follows the peak. And then our B bench is this kind of weak peak, and below that, we have, above the marl, we have our A chalk. Below this peak, somewhere in here is our C chalk. And then somewhere below or near the Greenhorn, we have our Codell sandstone. Another really interesting thing to note is how much internal faulting there is within the Niobrara Formation itself. And you can see the chalk is actually broken up a lot more than the overlying shale. So it makes it hard to easily map your chalk benches based on the 2 seismic events that you can easily map. So how do we haven't covered yet how you select attributes for your SOM. So we talked about how the SOM takes the attributes and creates a classification volume, but the geophysicist is still faced with selecting attributes. And this is sometimes hard to overcome as an interpreter because a lot of people have things they feel strongly about and their favorite attributes. But we go ahead and let the data talk to us. And we use principal component analysis to help us understand which seismic attributes that out of all the ones we've generated contain the most information, the largest variation and the most independent information. So I'm not going to go through PCA in depth, but just mention that this is how we go about selecting our attributes for SOM. And with that, I'm just going to show some of the PCA results out of Paradise for this study. This is an example of an eigenvalue and eigenvector chart that we have in Paradise. This is a specific inline that goes through a key well. So within Paradise, you have lots of different ways to look at the PCA results. You can look at specific inlines. You can look at ranges of inlines, and you can run your PCA over a wide window. You can run it over your whole volume. You can run it over a very focused window. In this case, we ran it over the zone that we were running, ultimately going to run the SOM on, our Niobrara to Greenhorn interval. I have to put my glasses on because this is small, but in eigenvalue, eigenvector 1, I've blown up what the top 3 attributes are in eigenvector 1, and these turned out to be sweetness, envelope, and relative acoustic impedance. And the percentage of their contribution to the eigenvalue is shown here, and you can see it drops off below relative acoustic impedance from 60-some% to 23%. So we took these 3 attributes from eigenvalue, eigenvector 1. Likewise, looking at eigenvector 2, we only see 2 prominent attributes. Those are thin bed and instantaneous frequency. So on and so forth, you ultimately arrive at a set of attributes that are contributing to your principal component analysis results. You don't get off the hook, though, just looking at charts. You really should go in and inspect these attributes that you're sending into the SOM to make sure that they look good, that there's not something really obvious like acquisition footprint or something that's dominating, because you really don't want to classify that, although you can. So here we are with some attributes, and I extracted them near the B chalk. So we're near the reservoir that we're most interested in. So this on the left is the sweetness from eigenvector 1, and on the right we have the thin bed indicator from eigenvector 2. Ultimately, we ended up with 9 attributes going into our SOM from 6 eigenvectors, and that's shown in this little table here. So let's dive into the results. Here is the original amplitude data, just slicing out our zone of interest. And this is through one of the wells that we had the petrophysical analysis, the petrophysics available for. And below you see an 8x8 SOM result going through the same well. The B bench is actually this yellow sequence of neurons, and it jumps right out at you. It's really well resolved. And the SOM topology we selected to to do this was chosen just visually after we had all the results and went in and looked, and this looked like a good one, the 8x8. And I'm going to get back on that. I bring that up because at this point, this work was done in 2018. It was a qualitative decision that was up to the interpreter. So zooming into the well, I want to point out the tie between the well and the seismic data here. So this sequence of this green is showing us the B bench in the seismic data tied in time. That's about 5 milliseconds or 5 samples in our SOM. Our SOM was sampled at 1 millisecond. In depth, that represents about 30 feet. But another interesting thing was really the reddish neurons seem to correspond to the maximum carbonate content in the bench, or in other words, that would be the sweet spot within that 30-foot reservoir. There's a reference for the petrophysical analysis that was performed. And then looking at a cross-section through 3 of the wells, there's a lot of information here that's quite interesting. The A bench itself is this dark blue neuron, which you can follow quite easily. The high TOC marl, which our petrophysicists called shale pay, you can see in this column, and here's our TOC curve. So this is a high TOC zone that they think could also be completed and produced. That's this kind of bright pink section. So we can see that. Our B bench you can follow. And down here where it gets structurally complex, you can still continue to follow your B chalk where you might not necessarily be able to resolve this. This is a pretty complex intersection of several faults when you look at that in 3D. Also, you can see there's structure within the bench that you're not seeing in the overlying shales, as we mentioned earlier. But the SOM makes it a lot easier to follow and a lot easier to get right on that sweet spot if you were planning a horizontal well. In Paradise 3.4, which came out in 2020, they've added the capabilities to extract the SOM at a well location. So I've made this cross-section through the 7 wells that we had our petrophysical results for, and this is pretty neat. I like looking at this. In our track on the left, we have gamma ray, and V shale is very faint, but in black and gray and black. Our depth track. This is my 8x8 SOM, and overlaying with the SOM is the volume of calcite curve. And there's a really nice match between the SOM neurons and the volume of calcite. We also have the TOC curve, followed by effective porosity and resistivity. I also wanted to point out when I go to do the statistics, I dropped this well off because there seems to be a bit of an issue with our porosity curve and with my V calcite curve. So in looking at this, I decided that V calcite was a better indicator of reservoir than V shale. But we also have our Fort Hays limestone here, which is high in carbonate. And so I would say that this SOM is responding to lithology and just the visual inspection, it's differentiating between carbonates and shales. And the vertical distribution is important. So when you start to try to build up, say, a statistical extraction of this, what I chose to do was not take because our neurons are repeating between our B chalk reservoir and our Fort Hayes, we want to make sure we don't pull that Fort Hayes into our analysis. So we added the capability to export these wells in LAS format. So now you can extract your SOM, you can extract any seismic attribute and export that as a log curve. And over the summer, we had a very talented intern named Yin-Kai Wang, who we had built a statistical tool to look at these extracted log curves. I'm going to show you some of his results. His work was based on a paper that actually was presented earlier today from Leal and others from PEMEX, where they used statistical measures to look at the relationship between SOM neurons and well data. So this is a histogram that's been extracted from over the entire Niobrara interval, and we put cutoffs on the V calcite and the effective porosity to flag the samples as either reservoir or non-reservoir. So you get a histogram and you can see, some neurons that are clearly not reservoir, and you have others that are very good reservoir. The program also calculates several statistical measures to tell you if there is a relationship between neurons in the presence of reservoir or non-reservoir. So in this case, we're showing a chi-squared table, and then it's showing us our chi-squared value and showing that there is a relationship between net reservoir and the SOM. So with that information in hand, you can go back into Paradise and look at these individual neurons in 3 dimensions. So I've done that for all of our benches. So I went back and did a histogram over just the A bench, and it showed me which neurons the wells sampled. We can plot just those neurons in Paradise, and you can see that I'm going to say depth, but in time and over large areas, these neurons are present. And so I think you could say that you can use these neurons to pick out your A bench over a fairly large area. Likewise, here's our B bench. And again, we have a completely different set of neurons that represent that. And again, they form a pretty tight vertical grouping that continues over most of the survey. And again, you can see the B is actually almost all reservoirs. So in this case, our chi-squared test failed because we don't actually have enough non-reservoir to make a valid test. So it's important to do the visual part as well as the quantitative part of this analysis. And then likewise, the C bench, we get a different set of neurons, and they are tightly spaced in the time domain and covering most of the survey area. And again, so we can isolate those neurons and say that those are representative of our C bench. And again, you can see the C chalk is mostly reservoir, and you can see how many neuron samples are in the C bench. So one of the other questions that Yin-Kai, our student, set out to help us determine is I looked at the 8x8 and said, hey, I like this 8x8 SOM. Is it really the best SOM though? So once we can statistically measure the SOM topologies through this method of extracting at the wells, you can look at, and this is hard to read the axis, but this is the 4x4 SOM. Here's our 8x8 SOM. Out here is a 12x12 SOM. And you can see the chi-squared value, the likelihood ratio, the Kramer's V, and the Bayes factor are all at their highest for the 8x8 SOM. So now we have a number that tells us that, yes, the 8x8 is really the best topology, but it also shows you can use 7x7. And interestingly, it goes back up at 12x12. So the well extractions are really good, really helpful for helping us calibrate our SOM results to our wells. But I do want to finish with a word of caution. I went and looked in Petrel with my full 3D SOM volume, and this is an example just over the B bench. And I looked at the neuron histogram for the entire 3D volume and what the distribution of neurons was. And we have 45 of the 45 neurons actually have data in the B-bench. But in our extraction at our 7 wells, only 19 of the neurons have data. So you need to go back when you see these kind of numbers and look in the 3D view and see if there maybe these other ones are hanging out at the fringes, or maybe we got something wrong in the extraction of the interval. But I went back into Paradise and I turned on just the 19 neurons that we had in the histogram. And you can see I have a hole right smack in the middle of the bench. So obviously there are some things missing that just relying on our well data, it's not picking up, it can't tell us the whole story. So you do need to go look at your full 3D seismic volume, I'll say, and determine what these neurons are, and also go back to maybe some of the wells that sample those neurons and see if you can see something different that's causing those neuron numbers to be different. And that brings me back full circle to the point we made at the beginning of the talk about supervised classifications versus unsupervised. The SOM will show you what's in your data, whereas the supervised is taking possibly what you have in your wells and trying to project that onto your seismic volume or get something out of it. But if something's present in the data that you're not counting on in your supervised classification, it could cause trouble. Okay, so in summary, we'll wrap it up. Seismic multi-attribute analysis is delivering on the promise of improving interpretations via the integration of attributes which we know respond to the subsurface conditions, and those can be stratigraphy, lithology, faults, fractures, fluids, etc. Statistical methods and SOMs enhance the interpretation process and can be easily utilized to augment your traditional interpretation, and utilize attribute space to simultaneously classify suites of attributes into sample-based high-dimension clusters. For our DJ Basin case study, we have resolved the primary reservoir targets, the Niobrara chalk benches, which are represented within 60 milliseconds of 2A time data, sampled at 1 millisecond, I should mention again. So we get that down to 1 to 5 neurons, which is 1 to 5 milliseconds. Converted to depth, that's resolving from 7 to 35 feet in thickness. And the Paradise visualization tools, including the 2D color maps and well log extraction tools, enable a lot closer ties to the wells. And quick acknowledgements, we thank GPI and Fairfield for their data set and the permission to show it. Yin Kai for his program and analyzing extracted SOMs. Sarah and Patricia are my co-authors on this, and Digital Formation for their petrophysical analysis. And with that, I'm happy to take any questions.
Just as a quick reminder, if anybody has any questions, you're welcome to put them in the chat or in the YouTube.
Oh yeah, I'll move my chat.
There you go. The YouTube comment stream.
Oh, thank you, Jay.
We'll give it just another couple of seconds.
Oh, I can take my glasses off again. I don't have to read that little table.
All right, with that, we're going to go ahead and close out. Remember, you can always go over to the Meet the Experts page, and Carrie is in the Geoscience Applications room there. So you're welcome to stop by and chat with her. Have a nice afternoon, everyone.
Thank you, Laura, and thanks for those who attended. Bye.
Hello, everyone, and welcome to our last presentation of SEG 2020. Yvonne will be talking today about connecting multi-attribute classification to reservoir properties. If you have any questions during the presentation, you're welcome to type them into the chat on Teams or the comment field in the YouTube live stream, and he will get to those as soon as he's done and answer those verbally. So without further ado, go ahead, Yvonne.
Thank you, Laura, for the introduction, and welcome to everybody. And as Laura said, I hope that you guys have an excellent SEG given the current circumstances. So here's my presentation. Challenges in interpreting seismic data are always present, and Geophysical Insights develop a machine learning classification that allows interpreters to deal with such challenges in a much different way. It takes interpreters away from the seismic waveform resolution limit to move them onto a multi-attribute classification that is defined on the level of seismic sample. As a result, interpreters can extract more geological information from seismic data. So in this presentation, I will show to you how we can leverage bivariate statistical analysis to connect the result of a machine learning classification to a reservoir property of interest for the benefit of a better reservoir interpretation. The algorithm behind the multi-attribute classification is the self-organizing maps sum. It is an unsupervised algorithm, which means it does not require any external information to guide the classification. Instead, the classification is a two-step process. It is cooperative and competitive to detect regions of high density in attribute space. And some of those natural clusters can reveal important geological features. Once the training is complete, all the multi-attribute samples are assigned to the closest winning neuron. And what follows next is just an interactive process from which interpreters make use of the 2D color map and the 3D viewer to reveal the presence of important geological features, like an example shown on this slide, in which my colleagues used geometric seismic attributes to reveal the presence of faults in the associated fracture systems. And this information is very important for the optimization of well locations in this area of Texas for the production of hydrocarbons. Among all the winning neurons that were used in this study, the most important were number 31, which reveals the presence of large faults here, over there, and here. Then neuron number 24, which denotes the presence of rocks that were not deformed by the presence of those large faults. And neuron number 14, which was interpreted to be acquisition footprint in the seismic data. This is another example that illustrates how the machine learning classification works. It is about a thin bed case study. And the first thing I want to draw your attention to is the following. Along this good well within a survey area, production comes at a depth over 10,000 feet. And we're talking about around 2.8 two-way travel time. At such time or depth, the seismic energy already lost a lot of joules. As you can see in this zooming, there is a tiny peak event associated with production. And because of that, it becomes almost difficult if not very well challenging, to try to infer what kind of geological body is behind this production. This slide I'm showing you two types of information. The first one is the amplitude data in the form of seismic traces. In order to avoid an overcrowded display, I'm showing you every fifth seismic trace. And as you start moving from your eye from the left all the way to the right until you reach the well, you see that there is only a very subtle amplitude changes from trace to trace to trace to trace. The second information is in the background, and is the result of the machine learning classification, which is done on a seismic sample level. So every time that you see a little rectangle with a specific color, like in here or over here, that means that that particular seismic sample got assigned to a given winning neuron. And because all those winning neurons have a specific color, then there is a sudden gain in geological information. If you put your eyes on your attention on the well location where the perforation is, and then we move from there to the left, you will notice that there is a specific grouping of winning neurons that has shape, and that is composed of a certain group neurons that grouping. Then if you move from the same point on the well to the right, you see a totally different grouping of neurons with a different as well shape. So then when my colleague used flattened time-slide views from the classification volume, she was able to interpret the reservoir to be an offshore bar. Now I would like you to take the time to see the strong correlation between the location of the producing wells and the discovery well, as well as all these wells which are characterized by poor production with respect to the extent of the reservoir body. The next step in the interpretation of classification results, at least in my mind, is to ask questions like how closely those neurons are related to reservoir properties. Perhaps a way to answer this type of questions is by using well cross-section displays like the ones shown on the left, from which we search for sequence of neurons and relate them to changes in reservoir property. Reservoir property can be characterized by one or several well-log curves. Although this exercise is very important, it still remains a visual inspection. In a published study by Leal and his co-authors, in which they use machine learning classification to characterize submarine slope fans in Mexico, they were confronted with the same situation. After they identified their best classification result, which is showing here in the background, they wanted to relate it back to a net reservoir property estimated from all the wells within the survey area. And they have a clever idea. They decide to use a well-known statistical tool in medicine, psychology, and social sciences that is a contingency table. And to build such table is quite simple. It only requires that for every neuron from the classification, you count his occurrence. In the section, the well path that corresponds to net reservoir, and then the section of the well path that corresponds to no reservoir within a window of analysis. And they did that for everything, for the remaining of the neurons, for all the wells within the survey area. Once you have this contingency table, then you have two categorical variables. The one dependent is the neurons coming from the classification, and the other two that represent the property of the reservoir that you want to characterize. Thereafter, the analysis was to determine if there exists a statistical relationship between the neurons and net reservoir. So I built on this idea to come up with a procedure upon which we can connect the results of a classification to a specific reservoir property. And I will show to you that in addition of having the ability to determine whether or not there is a statistical relationship between categorical variables, there is much more that we can learn from contingency tables. I will show you that we can learn about the distribution trends of the variables, as well as the relationships between variables of the same category. So for that, I will start by using the contingency table that Leal and his author obtained from the data, from their study. By using this graphical trend, the first graphical output, the first thing to do is to understand the trends that are in the data. So it's very clear from here that we can pinpoint what neurons can have an important occurrence with the reservoir property of interest. We can find out how many of those neurons are, and at the same time we can compare the occurrence for the property of interest against his counterpart. With this graphical display, the ideas are quite different. We want to understand how individual cells of the contingency table contribute to a deviation or departure from independence. And this concept is very important, because it will lead later on when we are going to use a statistical test for assess or evaluate the statistical relationship, if there is any. Because all these statistical tests, they check for two hypotheses. One, two categorical variables are independent, and two categorical variables are statistically related. With this graphical display, what you look for is for the size of the tiles, the colors of the tiles. The more darker you have, the more bigger those tiles are, the stronger is the indication that the data that you have at hand is statistically related. This is a graphic display produced from a correspondence analysis. This type of analysis is similar to principal component analysis in the sense that it takes the contingency table and projects it onto a lower dimension. Because the table we're using only have two variables along the column direction, the table gets projected onto one dimension. So I decided to do the following. The column points, net reservoir and no reservoir, are plotted along the y-axis. What we can learn from that is that these two are far apart from each other, which means they're independent, they're not confounding each other, and we want that characteristic from the table when the time will come to use the statistical test. Then all the row points, which are the neurons, are plotted along the x-axis. So now let me bring the interpretation that Leal and his co-author gave to all these neurons. Then we see that this type of plot brings forward groupings of neurons that has that have a geological significance. You have one group that represents the best reservoir rock, another one that corresponds to rocks with a storage capacity, and there is only one neuron sitting by itself that depicts rocks with lower storage capacity. This type of information wouldn't be so easily accessible by just looking at values of the contingency table. Now, when the time comes to measure whether or not there is a statistical relationship between two categorical variables, I propose to do a transformation of the original contingency table because of these potential issues. The first, this table may have cells with a 0 value. And that can occur when you have neurons that only exist when you have net reservoir. Or even you have other neurons that only exist when you have no reservoir rocks. So when you have those zeros in your contingency table and you need to compute the expected frequency in order to compute the statistical test, those expected frequencies don't make sense. You have a numerical value associated with them, but the corresponding observer frequency is 0. In addition to that, the statistical test may behave differently in the presence of cells with a 0 value. And even more, you may have a table that has so many row points, and because you have so many row points, you will end up by saying, yes, two categorical variables are statistically related. And that conclusion is just false because the result of that is just by the number of rows, which means just pure luck. So what I propose to do is to take the original table, convert it onto a confusion matrix that has this format. And then I define these rules in which true positive and true negative are just a count of how many rows for each of the neurons, their values is not equal to 0. Then for false negative and false positive, I just do the contrary. I count how many row points under net reservoir or no reservoir the cells have a value of 0. If I still end with a matrix that has zeros in one or in a couple of these cells, then I apply this correction. So in this slide, I explain how the procedure works. Let's focus on the cell in green for net reservoir. So in here, I will go and count how many row points I have under net reservoir whose value is not equal to 0. 1, 2, 3, 4, and 5. The 0 to the right is how many rows under net reservoir I have a value 0. None. The answer is none. Then I put 0 here. Let's move on to the cell in orange. I do the same, but for no reservoir. So how many row points I have whose value is not equal to 0? 1, 2, 3, 4, and 5. There you go. And the 0 to the left is just the same as before. How many rows there are under no reservoir with a value equal to 0? The answer is still none. Then I set 0, this 7. Because the presence of these zeros, then this correction is applied. And this is the final shape of the matrix upon which the statistical tests are computed. And I use two groups of a statistical test. The first one says either I accept or I reject the existence of a relationship between two categorical variables. And I have chi-squared and likelihood ratio. To understand the meaning of these values, I need to compare the measured value for chi-squared and likelihood ratio against a critical table, given the degree of freedom. And then I also consider the p-value. If the p-value is lower than 5%, then the results make sense. On the second group, this test also inform about yes or no there is a statistical relationship, but they offer an additional information. They also give a sense of the strength of the relationship. In this group, I have Bayes factor and odds ratio. So both of them, the value is bigger than 1, the stronger the relationship becomes. So all these 4 statistical tests shake hands and they say, yes, some neurons are statistically associated with net reservoir. Now, Leal and his authors, they use chi-square but on the original contingency table, and they reach the same conclusion. So that proves that process and proposing of reorganizing the contingency table is working. For the rest of the presentation, I will show you how the procedure works on 2 case studies. The first one, the focus was fractured chalk benches A, B, and C in Niobrara Formation located in northeastern Colorado. 7 wells were used. A net reservoir property was estimated by using volume shale and porosity with log curves. What you see on the right is the list of seismic attributes that my colleague used to perform a machine learning classification, and they determined that the best result is a sum with a topology of 8 by 8, meaning 64 neurons. So here is the obtained contingency table. All the cells that are in yellow indicate that you have an observed frequency of 0. Now, using this type of graphical displays now start making sense. Trying to understand what the value, individual values from such a big table is quite difficult. But by using this type of display, it's quite easy to see what neuron might be of interest because they have a relative association with property of interest. I can compare the occurrences for the property of interest against his counterpart. I can also, by the size of the dot, easily spot all these neurons. This one, and these 2 have a 0 count. And that's one over here. Since I'm using all data at once, it's quite difficult to understand what is the real size of the tiles in this plot. Nonetheless, just by looking at the number of the stripes that are in blue, in red, here, over there, and all over here, it is clear there is a strong indication. It is clear there is a strong indication that we are departing from an independent model. Now, if you remember, I have neurons whose observed frequency is 0, and they show a negative contribution over here, over there, and over here. And that is incorrect, because we know that the respective observed frequency is 0. And this is just reinforcing the need to do something with a contingency table that has zeros in his cells. Now, in this plot, once again, for the correspondence analysis, once again, we see the net reservoir and non-reservoir are far apart. Before we look more closely into this, let's have a zoom on this area of the plot. So now we can see that around the background rocks, the bench A has a much bigger presence in the contingency table compared to bench B and bench C. On the other hand, bench B and bench C never occur by themselves. And there is one interesting point over here, which I think might be an outlier for bench A. If that's the case, then I need to back again to examine the input data to make sure whether or not this is an outlier. However, this type of information couldn't easily be installed by just looking at the values of the big table, or the big contingency table that I have for this case study. Now, for measuring the statistical relationship between two categorical variables, I follow the procedure outlined in a couple of slides ago. So I count the number of times that net reservoir, the raw points for net reservoir has a value not equal to 0. Do the same over here and then over there for no reservoir. And now, because this table does not have cells with a 0 value, no correction is applied. And then I measure the statistical test. So here are the results for the first group, and then the results for the second group. One more time, for this study, all these four statistical tests indicate that there is a statistical relationship between some neurons and net reservoir. Then my colleagues push a little bit more in the envelope and decide to run several machine learning classifications by using different topologies, starting by 4x4 all the way up to 12x12. And then they estimated net reservoir property using 4 groups. The bar in blue corresponds to 1 well. The bars in orange corresponds to 3 wells. The bars in green correspond to 5 wells. And the bars in gray correspond to 7 wells. It is very interesting to see that chi-square, likelihood ratio, and bias factor mirror each other. In addition to that, as more data from the well is made available, as more neurons are used for the classification, the more these 3 statistical tests become optimistic, as saying there is a statistical relationship between 2 categorical variables. On the other hand, odds ratio is not influenced by the amount of data extracted from the wells, neither by the size of the topology used for the classification. On the contrary, it points out to a specific solution where it believes to, where it points to a classification with a topology 7x7, which happens to be close to what my colleagues determined to be the best classification result. The coincidence is very strong. For the second case study, the target was Cretaceous sand units deposited on stacked channels located in northeastern Colorado. The net reservoir was again estimated from 11 production wells, but using gamma ray law curves. On the right, you see the list of seismic attributes that were used to perform the machine learning classification. My colleagues determined this time that the topology of 4x4 is the best result, which is a total of 16 neurons. So here's the contingency table that I obtained for this study. The comments on the right are just to remind us that that table will come on different flavors. And because of that, we need to investigate the information that they carry so we can have a better understanding of the results when the time comes to measure the possible existence of a statistical relationship between 2 categorical variables. Using the same typographical display, here are some neurons associated to net reservoir. We can again compare the occurrences according to the property of interest versus his counterpart and make some decisions about it. We can use this typographical display to understand whether or not the data we have departs from a model of independence. This is still the case for this data set, given the relative size of the tiles in the colors. The plot from the correspondence analysis, again, indicates that net reservoir and no reservoir are far apart. And again, they're independent. Let's bring the interpretation of my colleagues about all these neurons. And we notice that the presence of groups. We have two groups where there is a combination of reservoir with siltstone in here, and over here. And also we have two groups made of one individual, or one member each. Siltstone over here and reservoir. So imagine that if I'm interested in looking into a new area where I would like to place my next well, perhaps I will be looking where neuron 16 in the classification volume is present compared to these two groups. I continue with taking the original contingency table and transform it onto a confusion matrix. Because I have zeros in these cells, corrections apply. And this is the final format after which the statistical tests were computed. So again, I compute the same group of statistical tests. This is the first, and here's the second. And all four agree to say that some neurons are statistically associated with net reservoir. Similar to the exercise in the first case study, my colleagues performed several machine learning classification using topologies from 4x4 all the way up to 12x12. Then net reservoir was estimated by using three groups. Bars in blue correspond to one well, bars in orange to 5 wells, and bars in gray to 11 wells. If you see in the chi-square and likelihood ratio, the bar blue, some bar blues are missing. That is because the associated p-value was higher than 5%, meaning that the test failed. Beside that point, we see one more time that chi-square, likelihood ratio, and bias factor, all of them mirror each other. They also tend to say, well, there is something going on in here, in this area of the plot, and in here as well. However, as you continue looking to your right, then you realize that no, as soon as more and more neurons were used to perform the machine learning classification, along with more and more well data, then all of three become more optimistic as saying, yes, there is a statistical relationship between two categorical variables. As ratio, one more time, stand by itself. There is no specific trend in the results. On the contrary, they clearly point out that there is a particular solution with a topology 6x6, which happens to be in a neighborhood of the best result according to my colleagues. As for conclusions, having the ability to bring together machine learning classification and reservoir property opens the door to the way how classification labels are perceived. Throughout the presentation, I mentioned neuron 16, neuron 2, 14, 31. With this type of analysis, we realize that those classification labels can carry reservoir information, such discovery should give us much more confidence on the classification result as we walk away from well control. another important aspect of this work was to demonstrate that there is a latent information on those contingency tables that we need to leverage so we can gain better insights into the result of the statistical test, because that's the end goal. We want to see whether or not there is a relationship between the classification outcome and the reservoir property of interest. And finally, as we understand better and better the power of those statistical tests, perhaps will we have another way, another way to support interpreters when the time comes for them to choose what is the best classification result for the benefit of a better reservoir characterization. I would like to thank Mr. Reynaldo Viloria and Mr. Fabian Rada at POGS for the valuable comments, suggestions, and discussions that I had with them around the topic of bivariate statistical analysis, as well as to my colleagues, Blaine, Kerry, Deborah, Sarah, and our sub-intern, Jean Kay, for sharing their machine learning classification work and results. And of course, I want to thank Geophysical Insights for this opportunity to be here and share my findings with all of you. If you have any questions, I open.
Very good, very good. Thank you very much, Yvonne. So we'll stay here on the line for a few more minutes and wait for you guys to post your questions in the chat or the comments field. Thank you very much, Fabian, for your kind words.
Thank you, Fabian.
All right, we'll go ahead and wrap it up. That presentation concludes our SEG live streaming presentations during the event. I hope you guys have had a wonderful past few days, and feel free to reach out to us on the myriad of contact forms that are sprinkled about, and we'll be happy to chat with you further. Have a great rest of your week.
Thank you, Laura. You too.
Thank you.